Hi guys, a very good morning everyone. Welcome to the session and welcome to the special class on antenna. Okay, so yeah, as I told you yesterday that in this particular session that's going to happen today, we are going to open up and discuss a lot of concepts from the very important topic antenna because probably this is one of the topic where you expect really good questions in EMFT, and this is also one of the topic where many students leave it. But if you want to be in the top zone, in the top funnel of the gate, okay, you definitely need not leave any important and difficult topic because okay, difficulties, those who are able to face, okay, they only turn out to be the toppers, right? Okay, so very good morning everyone. Come on everybody, quickly keep joining the session. Okay, keep joining the session, share the session to all your friends. Let us get started quickly. Yes, everybody. Very morning. Very good morning everybody. All right. Okay, so chalo. No, today only antennas, as clearly mentioned. Today's session is antenna. Okay, so let's complete that and let's discuss about the other topics. What you're looking for. Very good morning, everyone. Very good morning, everyone. चलो, so बढ़ते हैं आगे की तरफ. Let's get started. Others will keep joining. So antenna, very important topic. Let's discuss this today, and this is a regular introduction. Forget. So guys, the coming Sunday, 21st of January, you can appear in the BYJU'S National Scholarship Test. Yes, and you can avail up to 90% scholarships based on the performance in the exam, and you can appear at any time from 9 a.m. to 9 p.m. And the coming Wednesday, 24th of Jan, workshop, how to secure single digit rank in GATE at 7:30 p.m. to be taken by Dheeraj sir. Okay. Now guys, yes, let me again give you a reminder. Okay. On YouTube, okay, the complete engineering mathematics session, the complete engineering mathematics marathon. Okay, and since there are a lot of chapters in maths, so come 2 days, 20 and 21st January. Okay, set yourself ready. Okay, to maximize your marks in the engineering maths examination. 20 and 21st of January, the complete revision marathon. Okay, on the same YouTube channel. Do not forget to subscribe it. Okay, so and it's roughly around 15-17 days left for the GATE examination to begin. First of all, okay, that is tomorrow. This is Saturday, Sunday. Okay, this is Saturday, Sunday, but tomorrow, that is Friday at 5 p.m. First, I'll be having a small discussion with all of you. Okay, first of all, in the remaining time, is it really possible to go for maximizing the marks? And if yes, what are the things to take care to maximize score 13 out of 13? We'll have a discussion around that, and then we'll discuss Saturday, Sunday. We are completely discussing the maths marathon, maths revision. Okay? So guys, let's get started. Antenna, as you all know, the source for radiation. I mean, throughout the electromagnetics course, beginning you start talking about wave propagation. How does the wave propagate in free space? What are the different parameters of wave? What is the speed of the wave? What is the attenuation suffered by the wave? What is the phase change in the wave? What is the impedance? And a lot of things, like what is the power associated with any wave? Power is commonly defined in terms of pointing vector. Isn't it? Power is commonly defined in terms of the pointing vector. So we discuss pointing vector. Then a wave traveling in one medium to another medium. If a wave suddenly enters another medium, how it is going to be how it is going to be transmitted, how much part is reflected back. So all those things we primarily discuss, when we talk about wave propagation. Okay, and we talk about the propagation of wave in different materials, maybe conductors, maybe dielectrics, or in general lossy materials also. Okay, so of course, we study a lot about wave propagation, but basically how these EM waves are launched into any medium, are launched into space. Let's talk about free space. Okay, let's talk about let's talk air. Let's talk about wireless, for example. So how these EM waves, we know about the properties of EM waves. Okay, again, as I mentioned, attenuation, speed, phase, a lot of varieties we know about the wave. But how these waves are actually launched into the surrounding air, into the surrounding medium, and they are basically, okay, they are basically done with the help of the elements that we are going to study today. That is the antenna. Okay, the radiation or launching of the waves, okay, into the space is efficiently accomplished. Okay, now, okay, how antennas can be efficient radiators and what efficiency depends on all these factors we are going to cover today itself. Okay, so the launching or radiation of the waves into space is accomplished with the aid of these conducting or dielectric structures known as the antennas. Okay, known as the antenna. So whenever I say radiation, radiation means the process of transmitting energy, okay, into the surrounding. Now, do you know a simple transmission line open circuited at one end can itself behave as a good radiator? It can be a good source of radiation. How? Okay, can be good source of radiation. How? Okay, so let's talk about this. There are several points written, but ultimately once we go and discuss the internals, then you will see that yes, the antenna may be just nothing but acting like a transducer, matching a transmission line or waveguide to the surrounding medium, or vice versa as well. Okay, so let's look into these details so that you can understand others of them. Okay, so the following figure shows how an antenna is used to accomplish a match between the line or waveguide. Let me explain this. I'm telling you, transmission line itself, open circuited at one end, okay, can behave, okay, as a good source of radiation. Now, how is that? Okay, this simple picture shows that there's a source, okay, AC source, okay, fed to the transmission line, okay, and okay, the antenna responsible for launching the EM waves into the surrounding medium. Okay, now why antenna is a good radiator, we'll come to that, but first let us discuss some fundamental, then you will be more able to relate and all this connect all these points. Okay, like we are going to mention and study that antenna is needed primarily for two main reasons. One is the efficient radiation, okay, and one is for matching the wave impedances in order to minimize reflection. How are we able to match the impedance? What is the radiation resistance of the antenna? Okay, we'll keep looking into that. Ab dekho, transmission lines open circuited at one end. Okay, so let's open this picture. Basically, a generator, AC source applied to a transmission line, and I'm going to leave the transmission line open circuited at one end. Have a look into this picture here. Okay, so let's connect a piece of transmission line, one side to a supply, okay, to the generator, and one side it is open circuited. Okay, one side it is open circuited, right? Very, very good morning everyone, keep joining quickly. Okay, now if you see when I provide the source here, okay, when I connect it to the generator, okay, the voltage and current waves start traveling on the transmission lines, as we studied in the transmission line as well. Okay, so there will be traveling voltage and current waves on the transmission line. Okay, see, if you short circuit this transmission line at the other end, then there is no voltage difference here. But at the same time, if you connect it to any load, okay, why I'm not connecting to any load? If I connect it to any load ZL, the energy will be absorbed into that load. I don't want the energy absorbed into a specific load, into a specific medium. I'm trying to transmit or to launch the electromagnetic wave into the surroundings. Okay, so there are the two ends of the open circuited lines. Okay, let us say for a particular moment, this is as positive polarity, this is at negative polarity. Of course, there will be some voltage difference between these two ends. Okay, suppose this is at positive polarity, this is negative polarity, but because you have applied the AC source here, okay, this polarity also will keep switching. Maybe after some other moment of time, you may find that this is negative, this is positive. Maybe at some other moment of time, you may find that this is positive, this is negative, and etc, etc, etc. So what I'm trying to say is, at this open circuited end of the transmission line, there is always a voltage difference. Okay, and that voltage difference gives rise to the electric field as per consistency with the relation. We know electric field is given by negative of the gradient of V. So this voltage difference gives rise to what is known as the electric field. And because of the voltage difference, I can say that there is a field existing here. I can say that there is a field existing here. And where is this field traveling now? Okay, because I have left the transmission line open circuited, okay, this field is propagating into the surrounding. Surrounding means just air, because I have not connected any load, so that the energy is absorbed. So the energy is propagated or launched into the surroundings, that is the air. Okay, also there is the current wave traveling. Also, there is the current wave traveling on the transmission line. Okay, and the current flowing through a line will be giving the rise to the magnetic field around it. Okay, will be giving the rise to the magnetic field around it. Okay, so there will also be magnetic field present around this transmission line due to the current wave traveling over it. Okay, then eventually it was found out. Okay, so guys, idea today is I want to cover all variety of questions of antenna. I want to cover all type of concepts. Okay, derivations not important, so if otherwise we'll spend a lot of time. So derivation not important at this point of time, especially when 15-20 days are left. But all concepts, how it can be derived, okay, whenever required, at least the hint about derivation I will give. But all concepts, all theory part, all conceptual part also, plus the question practice we will complete today. Okay. Now, later on it was so derived experimentally that when you take the transmission line and bend it at right angles, it behaves even as more efficient radiator. Now, how do we define the efficiency? We'll come to that point also. How do we define the efficiency? We'll come to that point also. But yeah, it was so found that if you use this transmission line which is bent at right angles, have a look into this picture. What do I mean by bent at right angles? I take the similar transmission line, first of all, but at a particular point, I bend it at right angles. Efficiency observed in this case, okay, as experiments told us, efficiency obtained in this case was pretty much more. Now, how do we define the efficiency, which is a parameter? We are going to see that. Okay, we are going to see that. Right. Okay, so now I use a similar transmission line but bent at a particular point at right angles. Okay, this is the right angle bending. Again supplied to the similar generator, to the similar source, and once again the voltage and current wave, okay, will be traveling across this transmission lines. And once again, on a similar note, I can say that the two ends are still open circuited only. The two ends are still open circuited only, and at every point of time, okay, there will be a potential difference between the two ends. Okay, let's say one of them is plus, one of them is minus. After some time, this may be minus, okay, or this may be plus, etc. Okay, again this minus, plus, or this minus, etc. And because of the voltage difference, as I clearly communicated, there will be electric field. Okay, and that electric field is existing in the surrounding, that is lodged into the air, and this is what electric field. And also because of the current wave traveling on the line, there will also be the launching of the magnetic field around it. There will be the launching of the magnetic field around it. Okay. Little later I will define the efficiency. Okay, little later I will define the efficiency, but I'll give you a slight hint that, okay, this particular antenna, this particular element is radiating some energy into the atmosphere. It is radiating some energy into the atmosphere, and let us say the power that is radiated, okay, suppose I call it as P rad. Let us say the power that is radiated into the atmosphere. Now, what is the power radiated by any antenna? We are going to learn that. Okay, okay, we are going to learn that. Okay, don't worry, we're going to learn that. Okay, so the power that is radiated by the antenna, suppose P rad, very important parameter P rad. Okay, and there is a particular power that is input, because ultimately the transmission line is also supplied by a source, so it is also taking the power from this source. So there is a particular power, okay, which is fed to the antenna, Okay, it takes some power known as the P in, and it radiates some power into the atmosphere. Okay, the power radiated as against to what was input to it is known as the radiation efficiency of the antenna. Isko properly और आगे discuss करेंगे, but this is the hint I want to give about the radiation efficiency of the antenna. Okay, the radiated power divided by the input power. So that is what I'm telling. Then it was experimentally found that if you feed the same amount of power I mean similar source, if you take the similar source here as well as here, the power radiated turns out to be more in this particular case, and hence I can say that transmission line bent at right angle will be having better efficiency. And this particular structure now, okay, this particular structure, okay, is said to be a dipole structure. Okay, it's basically a dipole structure, okay, containing these two poles. These two poles are nothing, the two pieces of the transmission lines only. Okay, the two ends of the transmission line only. And these two poles comprises a name, and that is known as the dipole. Okay, so the first structure that you're looking into is what is known as a dipole antenna. What is known as a dipole antenna. Okay, acha, the power that is input to the antenna, definitely a part of it is radiated. Okay, now as per the law of conservation of energy, na? Okay, law of conservation of energy to apply karna hi padega. Okay, a particular power is radiated, and what about the other power? So you have ultimately connected this source, you have supplied the input power, okay, to a particular transmission line which is built up of conductors. Okay, and whenever there are conductors, there will be ohmic losses, there will be conducting losses because of the property of conductor, that any electromagnetic wave traveling in conductor will suffer losses. Okay, so because of the conductor, okay, which is building the transmission line, okay, which is building the transmission line, okay, there will be some power which is lost, okay, and we call it as loss due to simply ohmic loss due to the conductors of the line. We refer to it as ohmic losses, conducting losses, or simply known as the ohmic losses. Okay, right, so we can also write down the efficiency as power radiated divided by the power input, that is P rad upon PL. Later on we will convert this formula in terms of radiation resistance as well. For fashion, yes, anything can be done, Surajit, but primarily we started, this was the first discussion started taking a simple transmission line, but when it was bent at right angles, of course, when I say experiments were done, so it was done for other angle also, but when it is taken bent at right angle, okay, it turns out to be the most efficient case. It turns out to be the most efficient case, and that is why we consider now a transmission line bent at right angles, open circuited at both the ends, okay, as a device which can radiate energy into the atmosphere. And such an antenna, because it is able to radiate, it is able to launch electromagnetic energy into the atmosphere, okay, it will be considered as an antenna known as a dipole antenna because of these two poles of the transmission line, these two ends of the transmission line. Okay, when you look into a laboratory picture, this is how actually a dipole antenna looks like. Okay, this is a typical laboratory picture of a dipole antenna. Okay, look into it, everybody. I think this should make the things little bit more clear for you. Okay, the transmission line bent at right angles, and this is the supply. Okay, this is how it gets the supply. Everybody, this is what is the picture of a dipole antenna. The first very important thing, okay, even if you look into the GATE syllabus, okay, is about the dipole and monopole antenna. Okay, is about the dipole and the monopole antenna. Okay, we'll come to monopole also. Let's study the dipole part first. Okay, so let's talk about the dipole antenna. Any doubts, keep asking me. Okay, right. Now, the first thing that we need to study under the dipole itself is a Hertzian dipole. It is not a practical type of antenna, Hertzian dipole, because by a Hertzian dipole we mean a very, very small current element, a very small length that is less than or equal to lambda by 10, 1/10 of the wavelength. Okay, 1/10 of the wavelength. Yeah, that is one possible reason, Prabhanjan, but not the only reason. Okay. चलो अब देखो यहाँ पे okay, we start with one of the dipole. See, Ananta, dipole can be anything. Hertzian dipole is also a dipole, so yeah, Hertzian dipole is a type of dipole. Okay, then there will be other types of dipole, like very commonly half wave dipole is very important for you. Even if you talk about, from a GATE point of view, Hertzian dipole is very important. Only thing is, you are going to learn sooner that it does not radiate enough power. It does not radiate enough power, and hence it is not an efficient antenna, okay, because of the small length considered. Okay, but mathematically it is a very important element. Okay, for discussion wise, ideally it is a very important element. Okay, we start with a very small element having length lambda by 10, and then we need to talk about, suppose lambda by 2 dipole or any other dipole. We can assume any bigger dipole any bigger dipole comprising of such small Hertzian dipole, and we can integrate the fields and build up the bigger field. So mathematically this is very important. Practically it may not be that important, because again I'm repeating, it has a very small power that can be radiated, but for question also it is important. You can expect questions out of this. Okay, you can expect questions out of this. Okay, you can expect the questions out of this. Okay, yes, tell me clear everybody. Any doubts, keep asking me. Okay, let's keep on discussing and moving ahead. Right. Chalo, chalte. Okay, now let's talk about, yeah, here it is. Let me locate it very clearly. By a Hertzian dipole, we mean a very small current element, infinitesimally small current element, ideal, where the length is less than even, lambda by 10, less than or equal to lambda by 10. We are assuming that it is at the origin, okay, and it carries a uniform current. Okay, that is I naught cos omega t, I equal to I naught cos omega t. Let us assume that this dl, isko thoda clearly mention kar dete hain yahan pe. This small current element, okay, carrying the current I and having the very small length, even much smaller than this, okay, is located at the origin, and it is having the current that is I equal to I naught cos omega t. Okay, let's say this is my point of observation. Okay, and I am interested in what is going to be the field, electric field or magnetic field at this point due to this dipole. Now what is the procedure? I told you derivations will not be discussed in this revision, but at least the procedure. See, how do we actually calculate the power that is radiated? Procedure samajh lena. Please understand the procedure at least. Dekho, it's a very logical thing that we can connect here. Okay, the power radiated by the antenna is always calculated as the surface integral of the pointing vector. Is always calculated as the surface integral of the pointing vector, P average dot ds. Okay, where P average is known as the power density pointing vector. Okay, where P average, as we all know, is known as the pointing vector, time average pointing vector. That is known as what? That is known as the time average pointing vector. Okay, or basically the power density. Okay, the time average power density. Pointing vector always represents the power density vector. So it is basically time average power density vector, calculated in watt per square meter. Okay, now that means to calculate the power radiated by any antenna, okay, we need the pointing vector, power density associated. We need the power density associated. Okay. The P average, okay, for free space is given by mod E square by 2 eta, and if you talk about free space, eta will be taken as eta naught. Okay, later on we'll put the value. Okay, abhi eta rakh dete hain. So P average is given by mod E square by 2 eta in the radial direction, in the direction of the propagation of wave. Okay, in the direction of propagation of the wave. In general, the radiation, see, in general, where will be the electric or magnetic field radiated? In all possible direction. Now, it may not be true that in all possible direction we have the equal energy. So that is why we will come to radiation patterns also. We will come to directive gains also. Very important directive gain parameter. Very important radiation pattern. Yeah, how is the antenna radiating? Okay, thoda sa pehle basic samajhte, then we'll jump to radiation pattern. In which direction it is radiating more? Okay, a antenna will not radiate equally in all direction. A antenna equally radiating in all direction is known as what antenna? Anybody knows? An antenna which radiates equally in all direction is known as, that's just a concept. Practically it is not possible an antenna radiating equally, but does somebody know? An antenna radiating equally in all direction known as what? Okay, known as what? Known as what? The ideal to head is also given a specific name. Okay. So, normally antennas will not radiate equal energy in all direction. In some it may be more, in some it may be less. Okay. या आइसोट्रोपिक, करेक्ट, दैट इज व्हाट इज आइसोट्रोपिक एंटीना, करेक्ट है, ठीक है, आइसोट्रोपिक एंटीना विच रेडिएट्स इक्वली, दैट इज द आइडियल केस, उसका डिस्कशन भी करेंगे अलग से, ओके, बट इन जनरल इट रेडिएट्स सम एनर्जी इन ऑल डायरेक्शन, ओके, नॉट इक्वली बट इट रेडिएट्स एनर्जी इन ऑल डायरेक्शन, दैट मींस इट इज रेडिएटिंग द एनर्जी इन द रेडियल डायरेक्शन, दिस इज व्हाट इज द रेडियल डायरेक्शन ऑफ द स्फेरिकल कोऑर्डिनेट सिस्टम, राइट? Okay, so we take the power average mod e square by 2 eta along the direction of the propagation of wave, that is the AR. The pointing vector is always in the direction of propagation of wave, correct? So that is the P average, mod e square by 2 eta into AR. So that means to calculate P average, what I need is mod e. Okay, what I need is mod e. ठीक है, अब देखो, yesterday we discussed Faraday law. राइट, कल डिस्कस किया था ना हमने Faraday's law, as per the Faraday's law, and this was final Maxwell's equation also. This was the final Maxwell's equation. Now Hertzian is not isotropic. I'm telling you, na, none of the practical antenna is isotropic. Hertzian isotropic नहीं होता है. We will see the radiation pattern of Hertzian. Del cross E is minus del B by del T. Okay, or del cross ES is minus mu del H by del T. Okay, because B is equal to mu H. Okay, as per the yesterday's Faraday's law. Okay, correct. Del cross E is equal to minus mu del H by del T. Okay, now if you want to convert into the phasor form, इसको हमने phasor form में convert किया. Okay, I hope you all know what phasors are. Okay, so if I convert this into the phasor form, I get the equation del cross ES is equal to minus mu, the phasor of derivative of any quantity is known as j omega hs. Okay, so now we have del cross ES, okay, is minus j omega mu hs. Okay, so now this particular parameter mod e can be obtained if you know the electric field, that's the magnitude of electric field, and to calculate the magnitude of electric field, okay, we first need what hs is. Okay, so es can be obtained from here. How do we get hs? hs, as I told you, b is equal to mu h. hs is obtained as bs by mu again, ठीक है, hs के फॉर्म में बात करते हैं, and bs is further obtained as del cross as. Okay, yesterday we learned now what is the relation between magnetic field and the magnetic vector potential. What is the A? Magnetic vector potential, as we discussed yesterday also. This is what is the magnetic vector potential. Okay, question भी हमने solve किया था. Curl of A gives the magnetic field, right? Curl of A gives the magnetic field B. Okay, so del cross A is equal to B. Okay, so B can be obtained, okay, if we know the magnetic vector potential. Okay, the vector potential due to a line current element is given by the magnetic vector potential due to line current element is generally given by, let's put it mu naught because we are talking about free space only, mu naught I dl upon 4 pi r. Now, one important point here is, this is mu naught I dl by 4 pi r. Okay. Now, one important point is, normally we write mu naught I dl. What is this bracket I? देखो, this differential current element that I have taken here is ideal. This current element taken here is the ideal. Clear, everybody? This is ideal. Okay. But I am interested in calculating the field at a particular point. Okay. Now, what is the current? Since we are talking about voltage and current waves, what is the current at this point? We know that any wave is a function of space. Any wave is a function of distance as well. So, what is the current that you see at this point? ध्यान देना. It will be not only I naught cos omega t. It is known as I naught cos omega t minus beta r, right? Like if a wave traveling only in the z direction, traveling z distance, it suffers the phase shift of beta z. Here it suffers the phase shift of beta r because at this, coming to the point P, the wave has traveled a distance which is equivalent to r. It has traveled a distance which is equivalent to r. Okay, so omega t minus beta r. Okay, this is known as omega t minus beta r. Clear? I naught cos omega t minus beta r. Now, this, if you solve it, this becomes I naught cos omega. Okay, if I take omega common, so t minus beta by omega into r. Okay, now there is one formula, इसको मैं अलग से लिख देता हूँ dear. Beta is given by omega by u. One of the fundamental property, one of the fundamental formula for wave. Beta is given by omega by u. So there, if you have beta by omega, that should be equivalent to 1 by u. This parameter is 1 by u. ठीक है. अच्छा, now then you have r by u. Okay, if this is 1 by u, overall here what you have is r by u. What is r by u? R is the distance traveled by the wave, u is the speed of the wave. What I should call it as? The distance traveled by the wave divided by the speed of the wave is known as the time taken by the wave to reach the point P. It is the time taken by the wave to reach the point P. Let us suppose that time is t naught. Okay, this is the distance traveled by the wave divided by the speed of the wave. Okay, so this particular term, now becomes I naught cos of omega t minus t naught. Clear? Omega t minus t naught. This particular current, okay, the current here is definitely I naught cos omega t, but the current at the point P is I naught cos omega t minus t naught, a delayed current, or simply known as retarded current. The current will not be same at every point in the space, na? So when you want to consider the current at any other point, okay, it's going to be known as the retarded current, which is delayed with respect to time, okay, yeah, which is a phase shifted form of the current, you can say. And this current, that's what I call it as the I, retarded current. ये क्या है? I think yesterday, I don't remember the name, but yesterday somebody was asking about retarded current, na? Okay, this is the retarded current at the point P. Okay, yesterday, I think so, in the yesterday's class, somebody was asking about retarded current. This is what it is. Okay, the retarded current at the any point P has been taken, and that retarded current, okay, अब link क्या बन गया basically? What is a link basically? Okay, now I naught is given to you. Okay, the current I is given to you. Okay, with the current I, you can calculate the retarded current. With the retarded current, you can calculate AS. अब इसको पूरा reverse देख लेंगे. Okay, with the retarded current, you calculate AS. Okay, that is the magnetic vector potential. Once you know the magnetic vector potential, you can calculate HS. Okay, you can calculate HS. Okay, so magnetic field will be known there. Once you know HS, you can calculate ES. Okay, you can calculate ES. So number one, if you only want to know about the fields of any antenna, okay, it can be obtained by this process. HS or ES can be known from here. HS or ES can be known from here. Clear, everybody? Then using ES, okay, we can calculate the power density of the wave. Using the ES, using the electric field, we can calculate the power density of the wave. And if I know the power density of the wave, I can also calculate how much power it is radiating. Because the radiated power is the surface integral of this pointing vector. Okay, so this completely describes the process that how do we actually calculate the power that is radiated by any antenna. Okay, power that is radiated by any antenna. Okay. So process and concept we will discuss. Derivation and steps are not required because questions per time spent करना है. Okay, so after completing all these calculations at the far field, now what do I mean by far field? Of course, far field here means a distance which is large, but how large is considered to be far field? ये अलग से पता होना चाहिए. Let me take you towards that slide first. Okay, let me show you that first. Okay, what exactly when I mean by far field? Yeah. This is what it is. पहले इसकी बात कर लेते हैं. Far zone. Okay. The boundary between near and far zone. Okay. Given by 2d square by lambda. Given by the value that is 2d square by lambda, where d is known as the largest dimension of antenna. See, there can be different antennas. Okay, there can be dipole antennas, there can be monopole antennas, or maybe there can be loop antennas, there can be helical antennas, there can be different type of antennas. Okay, so based on parabolic antennas, okay, based on the antenna, okay, something, whatever is the largest dimension of that antenna is taken, and 2d square by lambda, okay, is the boundary between near and far. थोड़ा और डिटेल में चले जाए तो have a look into this one. Okay, the Fresnel's and the Fraunhofer's region. Sometimes you may get simple one marker question on this also. The Fresnel region and the Fraunhofer region. So what is this, dear? The Fresnel's and the Fraunhofer region. इसको देख लेना. Okay, so if this is the antenna element and having the largest dimension of D, suppose it has the largest dimension which is equal to D. Once again, let me say that this D, okay, is the largest dimension which depends on the antenna to antenna, or no doubt. Okay. Largest dimension. Okay, any distance up to 0.62 square root of d cube by lambda is known as the reactive near field. Any distance from 0.62 under root d cube by lambda up to the 2d square by lambda is known as the radiative near field. Okay, both of them, this is up in a sense up to 2d square by lambda you have the near field. A part of it is reactive, a part of it is radiative. But as per your syllabus, okay, all your calculations and all your discussions that is going to happen, even radiation pattern, radiation formula, we are going to discuss in the far field. Whatever is there for you is totally about far field. So any distance greater than 2d square by lambda is known as the far field. Okay, is known as the far field. Basically, the Fresnel's region. Okay. Chalo. So the formulas, I'm telling you the procedure I have told you. Following this procedure, okay, the formula that turns up for H5S. Achha, which formulas to remember, which not to remember, I will tell you that also. Okay, the formula that turns up is ultimately available in front of you. H5S is J I naught beta dl by 4 pi r sin theta e power minus j beta r. Okay, okay. Yeah, in the far field, basically 1 upon r term will come. That's what the next I'm going to highlight, Ananta. That is what is the next I'm going to highlight. Don't worry regarding to it. Okay. Chalo. Okay, so H5S turns out to be this formula, and then E theta ultimately got by the formula that I've told you, the Faraday's law. Okay, but eventually we all know that the ratio in the phasor form for two perpendicular or two orthogonal components of electric and magnetic field, that is E theta S divided by H5S, is known as the intrinsic impedance, and that is equal to the eta. That is equal to the eta. Okay, so E theta S basically is eta into H5S. To basically remember any one of the formula, other can be just obtained by multiplying by eta. Okay, so this is what we first of all get the field formulas, H and E. Okay, H is only and only in the azimuthal direction. Okay, there is no R component, there is no theta component. Electric field is only in the theta direction. There is no phi and R component. And okay, then the next step is, as I told you, what? Okay, next step is, using this we calculate P average, and using the P average we calculate the power that is radiated by the antenna. The power that is radiated by the antenna. Okay, so after solving, the power that turns out is I naught square pi eta by 3 dl by lambda whole square. But as I'm telling you that we are talking about launching a wave into the free space. Okay, so agar hum free space ki baat kare to eta is 120 pi. You must be knowing this value, 120 pi or 377 ohms. So when you put it as 120 pi, you get radiated power as 40 pi square dl by lambda whole square into the I naught square. Okay, now one very important point is, this is equal to the power that is radiated by the antenna. Okay, this is equivalent to the power that is radiated by the antenna. Okay, now let me take the picture once again. We are considering dipole antenna as of now. Okay, let's consider that open circuited line bent at right angle. Let me consider that same picture once again. We are into dipole discussion only. Only thing is, we have considered Hertzian dipole, means the length. This is known as the length of dipole, and the length of the dipole is very, very small. Okay, less than lambda by 10, less than or equal to lambda by 10. Okay, less than or equal to lambda by 10. Okay, so I just want to redraw that particular picture. Okay, now what we primarily discussed, okay, that is this particular antenna, okay, already discussed few minutes back, is radiating, okay, is radiating some power into the atmosphere, isn't it? This is radiating the power into the atmosphere. Okay. So it is not dissipated across any load, but it is simply a power radiated into the surrounding, into the atmosphere. Okay. Now let us assume, dear, let us assume that if this particular power was suppose absorbed in a particular load, in a particular resistance, if this was suppose absorbed in a particular load, okay, then what is the sort of picture that you might have? What I mean to say is, suppose these two ends of the antenna, these two ends of the dipole antenna were connected to some fictitious resistance. Okay, were connected to some fictitious resistance. Okay. We know that this dipole antenna is radiating some power into the atmosphere, but now let us imagine, okay, it's a imaginary, it's a fictitious resistance. Let us say that across the two ends of the dipole, I connect a fictitious resistance. Then what is the power dissipated in this resistance? then what is the power dissipated in the resistance? That is equal to the power that is being transmitted across the end of the antenna. And then I can say that the power radiated is equal to half I square R if I use the peak value of the current. So what is the current you have fed to the antenna? As I've told you, we have taken the current I naught cos omega t. The peak value of the current is I naught. Okay, the peak value of the current is I naught. So half I square R. Okay, why I'm using the half I square R? Because I've used the peak value, not the RMS value. Okay, not the RMS value. Okay, so half I naught square R rad. If this power was radiated in a fictitious resistance, this is no physical resistance placed here, but we are just imagining that there is some power radiated, and if that power suppose is dissipated in a resistor, what is the value of that resistor is known as the radiation resistance. What is the value of that resistor is known as the radiation resistance. One very important question here, radiation resistance. And it's not 73 here, Jashwant. 73 is the correct value, but aage aayega wo. Here it's not 73. Okay. So if this power was dissipated in a resistor, okay, what is the value of that resistor which is going to dissipate the same amount of power? That resistor is known as the radiation resistance. Okay. So that's what it is equal to a power which is dissipated in a fictitious resistance, and that fictitious resistance is R rad, which is going to be known as the very important parameter known as a radiation resistance. Known as the radiation resistance. So as I told you, power is half I square R, I naught square R, because I'm taking the peak value. Then we have the formula for P rad. No need to remember the P rad formula, but just compare it to this P rad. Now I compare it to half I square R. Half I square R. I will be getting the value of the R. Okay. And after solving it, what is the value of R? I get very, very important formula, 80 pi square dl by lambda whole square. 80 pi square dl by lambda whole square. The power radiated is 80 pi square dl by lambda whole square, where dl is the small length of the antenna, rest everything is constant. Okay. Most commonly, the length is given in terms of wavelength. Otherwise, if not, length absolute may be given, frequency or wavelength can be given, something can be given. Okay. And it is 80 pi square. Okay, 80 pi square dl by lambda whole square. When it is 40 pi square, I'll tell you hint. You'll understand slightly later. 40 pi square कब use होता है वो भी बता देता हूँ. ठीक है. So it is given by the formula 80 pi square dl by lambda whole square. It is given by the formula 80 pi square dl by lambda whole square. 80 pi square dl by lambda whole square. Everybody okay? 80 pi square dl by lambda whole square. Very, very important. Okay. Now there are two things. Okay. There are two things. The length is not lambda by 2. That's what is the length already mentioned. We are talking about Hertzian dipole, which has a very small length less than or equal to lambda by 10. Abhi questions bhi karenge. Okay. ठीक है. Questions bhi karenge. Don't worry. ठीक है. So what are the important formulas I suggest to remember from Hertzian dipole? Okay. After all this discussion, okay, one formula is the magnitude of the fields. Okay, don't remember the complete complex formula, but when you take the magnitude, see, mod of j is always 1, mod of e power j theta is also 1. Okay, so if I write down this magnitude part, if I write down this magnitude form, mod of h phi s, what is mod of h phi s? I naught beta dl sin theta. देखो, j is magnitude is 1, e power j theta is 1. So I naught beta dl sin theta is divided by 4 pi r. Is divided by what? Is divided by the 4 pi r. Clear? Correct. Power radiated or radiation resistance you're talking about, Rahul? And if it is between L by 50 to L by 10, it is Hertzian dipole. We cannot say it is a fixed value, Rahul. Okay. Okay. So I naught beta dl sin theta divided by 4 pi r. Okay. And then if you want to remember E theta, okay, don't remember separate formula, just multiply by eta. Okay. Eta mod h phi s. That's it. Eta mod h phi s. Okay. Remember mod h phi s. I naught beta dl sin theta divided by 4 pi r. Okay. These are the formulas to be noted. जहाँ से numeric आ सकता है. Although not very much, this is also not very much important, but sometimes numericals can come up on the strength of the fields. Okay, from the strength of the fields. That's a very important, very, very important is, okay, from this discussion is that whether you talk about mod E or whether you talk about mod H, because we are talking about far field, okay, all our discussion is in the far field, okay, very clearly that the strength of the field as compared to distance is inversely proportional. It is inversely proportional. Okay, so it is proportional to 1 by r. This is a point to be noted. Some logical questions are also, expected on this. Okay, the strength of the field in the far field is inversely proportional to r. Directly r, well, 1 upon r, not r square, not r cube. So if you derive it completely, you get r square and r cube terms also. I'm telling you, when we derive it step by step, we get some terms of r square and r cube, but in the far field, they are negligible. In the far field, they are negligible. And finally, this is the formulas that turns up in front of you. Okay. Now, so from Hertzian dipole, this one formula, the strength of the field and the radiation resistance is extremely important. इस पे तो direct question आते रहते हैं. Okay, the radiation resistance 80 pi square dl by lambda whole square. Clear? We'll take questions together. Let us complete some more part. Let us complete the some more part. And I hope you have got the concept also of radiation resistance. There is no physically connected resistance, but it is an imaginary or fictitious resistance. If it was connected and the entire power dissipated in this, then what is the value of the resistance? Okay, which will dissipate the same amount of power which is transmitted by the antenna. Okay, hope that definition is clear to you. And it has been obtained 80 pi square dl by lambda whole square. ये far field वाला हमने condition देख ही लिया था, far zone and near zone. Okay, Fresnel and Fraunhofer region. This far field is the Fraunhofer region. अच्छा, then this one is the Fresnel's region. The radiative near field. This one is known as the Fresnel's region. ठीक है. So if they sometimes ask for a given antenna, what is the Fraunhofer region, that is equivalent to what is the far field region, and that is given by 2d square by lambda. The distance greater than 2d square by lambda, d is the largest dimension of the antenna. Now let's come to the next very important, that is the half wave dipole antenna. Alright, we are discussing dipole only, but I am taking the half wave dipole antenna case. I am taking the half wave dipole antenna case. Okay, half wave. As the name itself says, what was the length considered earlier? This was a very small element. Okay, अच्छा देखो, एक simple सा example लेते हैं. Okay, say for example, dear, if I take, as I'm telling you, DL is less than equal to lambda by 10. If I take DL equal to lambda by 20, so the boundary wala bhi nahi. If I take the DL equal to lambda by 20, guys, what is the radiation resistance? What is the radiation resistance? Then it will be given by the formula 80 pi square dl by lambda whole square. Now dl itself is lambda by 20. Okay, so lambda definitely cancelled, so we have 80 pi square 1 upon 20 square is 400. Okay, so eventually the radiation resistance is a very small quantity, pi square by 5, approximately 2 ohms. Pi square is approximately 10. Okay, so it is approximately 2 ohms. What is the radiation resistance you get? Okay, a very small value, 2 ohm. And eventually, guys, you should know that if a particular antenna has a smaller radiation resistance, the power that it is going to radiate is correspondingly small. Smaller length means smaller R rad, eventually meaning the small power radiated. Okay, such a Hertzian dipole is not capable of transmitting sufficient power into the atmosphere. Okay, that is why conceptually it is an important antenna, because using this antenna, different types of antennas are studied, integrating this part. Okay, but on a whole, individually, Hertzian dipole practically is not that important because of the smaller value of the R rad. Okay, eventually, dekho, why I'm focusing more on R rad? As I told you, power is given by, what is more important is power radiated. But the power radiated is I naught square into R rad. Half I naught square R rad. I naught is the supply current. Okay, that does not depend on the antenna. That depends on you. You can give any supply. But this is what is the inherent property of the antenna. That is why we focus more here. Eventually, our interest is radiated power, but we focus more here because this is the parameter that depending on the antenna. Like here, it depends on the length of the antenna. Okay, here it depends on the length of the antenna. Clear, everybody? That is why R rad is very important parameter. Okay, it's one of the characteristic property of the any antenna, not only Hertzian dipole. It is one of the characteristic property of an antenna, radiation resistance, because we can simply say that higher the radiation resistance, higher will be the power radiated by the antenna for the same supply. Okay, for the same supply. Okay, so suppose you feed the antenna by a 500 milliampere current. One of the antenna has radiation resistance of 2 ohm like this. Now suppose if I give you an antenna which has radiation resistance of 73 ohm. Of course, who is going to radiate more power? For the same current supplied, who is going to radiate more power? The one having the more radiation resistance. Okay, so this is what is the property of antenna. Okay, that is why we are focusing more here. More R rad will be equivalent to more power radiated by the antenna. Okay. So this is typically very small value. This is typically a very small value. Okay. So now we come to, ये पढ़ लिया था, now we come to the next important dipole antenna, still in the dipole, but such that the length of the dipole is lambda by 2. ठीक है. So yes, Bhanu, why 40 pi square by lambda na? Just ask me after some more time. You will automatically get it once I complete the monopole part. Okay. So remind me there once again. Okay. एक बार monopole वाले discussion पे आ जाएंगे, then I think it will be automatically understood. That is for Hertzian monopole. मैं लिख देता हूँ यहाँ पे. I will write it for safety. I'll write it for safety. Okay, so that I don't forget. But why it is half, I'll tell you. This is Hertzian dipole. Dear, if you have a Hertzian monopole, if you talk about Hertzian monopole, okay, then when I talk about the mod h phi, yeah, simply mod h or mod e, okay, they will have similar expression. इसमें कोई difference नहीं आएगा. Okay, that will have similar expression. Okay, but radiation resistance will be halved, and that will be, rather than 80, it will become 40 pi square dl by lambda whole square. एक बार अभी लिख दिया, इसको थोड़ा सा बाद में समझ लेंगे. Because I have not told you what monopole is exactly going to be. But once I tell you the monopole, after half wave dipole, I will take the monopole only. So there it is understood why the radiation resistance become half. The power radiated will become half. That is why the R rad will become half. Even though we have the similar expression of E. ठीक है. चलिए तो इसको नोट कर लीजिए. Question इसमें भी आ सकता है. The formula is saved for you now. Okay. So half wave dipole antenna. Okay. The antenna whose length is half of the wavelength. That is how it gets the name half wave. Okay, the length is half a wavelength. L is equal to lambda by 2. So now we have a fixed length. Okay, not like less than equal to lambda by 10. A fixed length, that is lambda by 2. So this length, when I mean fixed length, this is what is lambda by 2. Correct? This is what is lambda by 2. Okay. So it consists of a thin wire fed or excited at the midpoint by a voltage source connected to the antenna via transmission line. Same like dipole I explained you. Okay, what dipole means? Okay, so basically now the procedure is still the same, guys. There is no change in the procedure of deriving it. Okay, the procedure that I told you is the same procedure going to be applied. Okay, retarded current, magnetic vector potential, magnetic field, electric field, power density, power radiated. Okay, power radiated. Okay, so after solving it up, okay, after solving the derivations, okay, we come up to the conclusion that the radiation resistance of this antenna, now because it has a fixed length, okay, lambda by 2, okay, so it will be getting a fixed radiation resistance, that is 73 ohm. पहले इसके radiation resistance की बात कर लेते हैं. Perpendicular, this one. When I say length, ये वाला length, Prabhanjan. Okay, this length. This is what the dipole is. Okay, so when I say this length, this is what is lambda by 2. This length is known as the lambda by 2. Clear, everybody? This is the length which is known as the lambda by 2. Okay. Okay जी. हाँ जी, ठीक है. Yeah, so this is the length lambda by 2. Okay. So देखिए, the radiation resistance of this antenna, okay, again by 2 par p rad by not. First we calculate p rad, okay, by integral p average ds. Okay, p average again by mod e or mod h. Mod e or mod h की बात भी कर लेंगे. Ultimately the radiation resistance, it's a quite significant value now. That turns out to be 73 ohm. That turns out to be 73 ohms here. And guys, this is the fixed value to remember. Lots of times you get directly question on this. Okay, radiation resistance of half wave dipole or quarter wave monopole. Next monopole पे आएंगे हम लोग. Next we are going to come to the monopole. Yeah. So total input impedance also can be calculated, but not very important. The total input impedance of an antenna is Rn plus jxn, where Rn is R rad for lossless antenna. Xn is 42.5 ohms. Okay, Xn. Okay, the reactance part is 42.5 ohm. So the total input impedance of the antenna is 73 plus J 42.5 for a dipole antenna. Although this is not very important, but the R rad part, typically you must remember, that is very important. Okay, for very important. Okay, so for lambda by 2, this is what 73 plus J 42.5. Quarter wave monopole. So where are the field expressions? ये भी hang कर रहा है आज. Where are the field expressions? I think they are missing. Okay, एक बार लिख लेते हैं. Okay, no issues. Okay, so once again, after deriving by the same procedure that I have told you, we get mod h phi s. Okay, again the magnetic field will turn out to be in the phi direction. Okay, the mod h phi s here turns out to be the formula I naught cos of pi by 2 cos theta is divided by 2 pi r sin theta, and if E is required, E theta will be, once again, don't write down the expression once again, it is just eta into mod h phi s. It is eta into mod h phi s. So I naught cos pi by 2 cos theta divided by 2 pi r sin theta, that is what is going to be the magnitude strength of the field here. Okay, now once we have the mod E with us, okay, just a second. Just a second here. I think there is some battery issue. I'll get it corrected. Theta क्या है अभी चलो वो भी explain कर दूंगा. Okay, what exactly theta is? Theta is the theta of the spherical coordinate system, Manaswi. Okay, but if you have forgotten, I'll come to that also. Don't worry. Okay, so these are the expressions also told. Now let me come to monopole antenna. Guys, just a second. I need to get it corrected. I think the pointer is not working. We'll be disturbed a lot. Just allow me 1 minute. So check करते हैं. Just wait on, dear. Hello. Okay, yeah. Chalo, what happened, Prabhanjan? Chalo, so you have called for a new battery. It's battery issue only most likely. Okay, so by the time, let's continue however we can. Okay, thoda manage karenge. Let's not stop. So I have given you the expression of the field. Okay, then we have the radiation resistance, and then let us come to the quarter wave monopole antenna. Now the idea is the length of this antenna is lambda by 2. The length of this particular antenna is lambda by 2. Okay. is lambda by 2. Now say for example, even if you consider some frequency, suppose if I talk about a very common FSM frequency, okay, approximately let's take a frequency 900 megahertz corresponding to the FSM cellular frequencies. Okay, what is the lambda corresponding to it, dear? C by F. Lambda corresponding to this is C by F, and C is particularly 3 into 10 power 8 divided by 900 into 10 raised to the power 6, and becomes how much? It becomes 1/3. Okay, it becomes 1/3. That means 0.33 meters. Okay, that is, let's say 33 centimeters. 33 centimeters. Okay, primarily 33.3 centimeters. So for such a frequency, when you calculate the length of the antenna, lambda by 2, okay, that length is approximately 16.67 centimeter, a pretty large value. Okay, especially even if you go to the very, very older phones also, okay, you know, you might have seen the old Nokia mobile phones having, you know, like the cordless phones having the antenna connected separately over the top. ये पॉइंटर तो नहीं खराब हुआ है, पॉइंटर एकदम सही चल रहा था, बहुत ज्यादा प्रेस करना पड़ रहा है ऐसा हुआ। चलो ये चेक कर लेंगे फिर बाद में। Looks like some issue with the pointer itself. Okay, so now typically under those cases, what I was telling, sorry I was interrupted, but okay, so typically under the cases where we would like to maintain the same field expressions as I mentioned here, if we want to have the same field expression without okay, able to bear a big length, okay, we can minimize the length to half of it. That is, it can be made somewhere around 8.3 or something. It can be minimized to half of it. Okay, maintaining the same field expressions if we consider the quarter wave monopole. If we consider what is known as the quarter wave monopole antenna, as the name itself, rather against a dipole, it's going to be a monopole. Okay, having a single pole. Now, look into it. What is the quarter wave monopole? Which is just 1/2 of a half wave dipole. This consists of a 1/2 of a half wave dipole antenna located on a conducting ground plane. Okay, located on a conducting ground plane. And dear, whenever there is a conducting ground plane, you remember something we learned yesterday also. Whenever there is a conducting ground plane, okay, we apply the concept known as the method of images. We have the concept that is coming up in the form of MOI, method of images. Okay, so this is the infinite conducting grounded plane. Okay, infinite means very large grounded plane. Okay, and this is only one pole of the antenna. See here, the total length is lambda by 2, but there is no antenna here. Just forget it. So the length of this much of the portion, Okay, when I talk about this much of the portion, this much has the length which is equivalent to lambda by 4, half of the previous case. Okay, it is fed at the base. It is fed at the base with some supply as shown here. It is having a length lambda by 2, but the important point is it is located above a conducting ground plane. Now, conducting ground plane, method of images. Yesterday only we discussed. What does method of images say? Ki whenever there is any source located above a conducting ground plane, you can remove the conducting ground plane. Okay, you can remove the conducting ground plane and you can replace with the image of the original source, with the equivalent image of the original source. Okay, so there is only one pole, we call it as monopole, but when we solve it, okay, we remove the plane. Physically we can't remove it, but to solve the field equations, we remove it and we get another image of it. And once you consider with the image, okay, the total length of the actual source plus the image then becomes lambda by 2. So equivalently, when you're trying to solve the field equations, okay, you will be considering this particular structure, which again looks like dipole, which again nothing looks like dipole. Lambda by 4 plus lambda by 4 gives you the lambda by 2. Okay, the appearance is very similar to that of dipole. Okay. These antennas are also very commonly used in the vehicles, automobiles, okay, for the FM antenna. Okay, say for example, I take the frequency, the frequency range for antenna is, it starts with 87.5, goes up to 98 around so, right? If you take any particular, suppose 100 megahertz bhi le liya. Okay, if you take it as even 100 megahertz, okay, the lambda, okay, which is 3 into 10 power 8 divided by 100 into 10 power 6, that becomes 3 meter, and then the lambda by 4 is 0.75 meter. If you take lambda by 2 here, okay, if you take the lambda by 2 here, that's 1.5 meter, and 1.5 meter of antenna installing on a car is again a big piece. 0.75 meter was still considered, and these were, okay, initially installed on the cars. Okay, now if you zoom this picture, I think iska zoom picture bhi hoga yahan pe. If you zoom this, nothing. Okay, that is what you see. This point, this is the supply point. You see this point, this is the supply point. As I told you, that particular antenna is fed at the base, okay, with the supply. Okay, and this is the length. This is the length which will be equivalent to the lambda by 4. Okay, a lambda by 4 monopole, okay, a quarter wave monopole, which is base fed with the supply frequency. This is what we are discussing right now. Okay. Right. Now, as I told you, because of method of images, we get a picture equivalent to that of a lambda by 2 dipole, Okay, so field expressions, here field expressions are there. I think wahan pe miss ho gaya tha. The similar field expressions do come up here. But what you have to again remember, guys, you have to again remember the magnitude of them. I'm getting a lot of trouble with the pointer, but okay. So I'm not writing the expression again, but mod h phi s or mod eta s. Dekho, iska magnitude nikalo. J magnitude is 1. Okay, e power j theta magnitude is 1. So what is left? Okay, I naught cos pi by 2 cos theta by 2 pi r sin theta. Yahi to maine aapko bataya tha. Okay, so it's going to be similar to that of, it is nothing but similar to that of dipole antenna. Because of the method of images, it is similar to that of dipole antenna. But will the radiated power be also similar? Okay, the radiating power will also be similar. Okay, no. That conducting plane, Ananta, is within it. Okay, the base of it, it's a conductor. The conducting plane, okay, as compared to the, see what it is basically, the dipole antenna is basically comprising of a thin wire, and with respect to thin wire, okay, this particular conductor is very large in extent. Infinite we put mathematically, but there is nothing like infinity. It's always something large with respect to another quantity. Okay, so that, okay, grounded plate, that conducting grounded plate is supplied, it's available here. Okay? So this is similar to dipole, but will it have the similar radiated power? Will it have the similar radiated power? Or can it have the similar radiated power? Dekho na. The power that it is going to radiate, ultimately there is a grounded plate. Okay, this is the supply point, and this is your monopole antenna. This is your monopole antenna. This is definitely located above a grounded plane. Okay, can it radiate the same power? Although it has the same, okay, although it has the same expression for mod E, means you will have the same expression of P average also. The power density will also be same because power density is mod E square by 2 eta. The power density will also be same. But when you take the radiated power, that is known as the surface integral. That is known as the surface integral of the power density. And now you are going to perform the surface integral over this above surface only. Because the power is radiated above. Okay, this is the infinite grounded plane. There is no power radiated below. Whatever is the power that is radiated above, that is radiated in the upper hemisphere. Okay, it is radiated in the upper hemisphere. Okay, so this integration to be done, integration is done only for above hemisphere. Okay, that is why even though the power density is same, the radiated power will be half that of dipole antenna. Dipole ke half aayega. And if the radiated power is half, the radiation resistance will also turn up to be half. Okay, radiated power पिछली बार 36.56 था, it is 18.28. No need to remember this value, but this is the value to remember. The radiation resistance, nothing. It is, remember 73 by 2. Remember it as 73 by 2, 36.5 ohm. The radiation resistance will be 36.5 ohm. And by the same token, the reactance part, which was 42.5, here it is 21.25. Although this is not the important value, but the radiation resistance, direct important value you should remember. So it will be 73 by 2. Okay. So expression of E will be same. Expression of field is same, Prabhanjan, for half wave and quarter wave. Okay, but the power radiated will be half and the radiation resistance will be half of that of dipole. The 73 by 2, 36.5 is what you are expecting here. 36.5 is what you are expecting here. Okay, chalo. Let's take some numerics here before we move forward towards the patterns and all. Chalo, kar lete hain isko. Tell me, dear. An antenna can be modeled as an electric dipole of length 4 meter at 3 megahertz. If the current is uniform over the length, then what is the radiation resistance? So before you tell the radiation resistance, you should know some important parameter, that is the length. Okay, what is the length of this antenna? It has length 4. Okay, but at the frequency 3 megahertz. So what is the lambda? Lambda is C by F. Now we can calculate that lambda. C is 3 into 10 power 8 and the frequency is 3 megahertz, 3 into 10 power 6. So lambda here is basically 300. Am I correct? Yeah. Sorry, 300 nahi, 100 ho gaya. 3 cancel 10 power 2. So lambda is 100. Okay. So what is length? It is 4. Okay. 4. With comparison to lambda, how much is the length? Pehle ye dekh lijiye. When you compare it to lambda, how much is the length? Lambda is 100, length is 4, so that is 100 by 25, basically lambda by 25. So the length that is given to you, okay, let me call it as the small length now, because it is very small as compared to the wavelength, lambda by 25, and whenever the length is less than equal to lambda by 10, okay, that particular antenna element is known as what? That is a Hertzian dipole element. Okay, that is a Hertzian dipole element. Okay, and then accordingly, because it is Hertzian dipole element, okay, you will apply the radiation resistance formula as 80 pi square dl by lambda whole square. So it's going to be 80 pi square. Okay, dl by lambda ho jayega 1 by 25, basically lambda cancelled. So you have 80 pi square by 25 ka square, which is 625, approximately calculating the value. 1.26. 1.26 ohm. The correct answer is B here. The correct answer is B here. Okay. Bhanu monopole. Dekho. So similar logic you apply na. I've already discussed the Hertzian dipole. Similarly, what will be a Hertzian monopole? Okay. A dipole of very small length, less than equal to lambda by 10, as I mentioned, located above a conducting ground plane. Orally sun lena. Okay. So if you take, okay, Similar to this, this was lambda by 4. But similar to this picture, if you again take an infinite conducting ground plane and over it you take an antenna element which is having a very small length, okay, that infinitesimally small length antenna will be known as not quarter wave, will be known as a Hertzian monopole. Small length means it is the Hertzian concept. Okay, because you take only one side above a conducting ground plane, that is a monopole. So that will be a Hertzian monopole. But because it is again located above a conducting ground plane, same idea like quarter wave monopole, that is the Hertzian monopole. Okay, a small current element located above a conducting ground plane, but when you go and solve it, to solve you remove the conducting plane, you replace by image charge. When you replace by image charge, monopole and monopole, they combine and they make a dipole. So the field expression will be same as Hertzian dipole, but what will be half? Field expression same hoga as discussed earlier. Okay, but what's not same? The power radiated will be half, because again the integration will be over the upper hemisphere. Okay, that is why the radiation resistance will become, formula already I told you, radiation resistance will become 40 pi square rather than 80 pi square, 40 pi square dl by lambda whole square. Okay, इसकी जगह बस 40 आ जाएगा. Okay, hope you have got it. ठीक है जी. Okay, chalo, next question. Have a look into it. A magnetic field strength of 5 microampere per meter is required at a point on theta equal to pi by 2, which is at 2 km from antenna in air. Neglecting ohmic log, how much power must the antenna transmit if it is a Hertzian dipole, half wave dipole, quarter wave monopole? There are 3 different cases. Tell me what can be the answer for it. Okay, tell me. Come on, everybody start solving. अभी मैं आ रहा हूँ ब्रेक में. आप चले जाते. नहीं मैं आ रहा हूँ, ब्रेक में आ रहा हूँ. Okay, chalo. So I think my problem is also sorted, so I can take it comfortably. A magnetic field of 5 microampere per meter, okay, mod H, is required at a point theta equal to pi by 2, which is at a distance 2 km from an antenna in air. Okay, so R is 2 kilometer. Okay, theta is pi by 2. Neglecting ohmic losses, how much power might the antenna transmit? Okay, power transmitted, power radiated by the antenna. If it is a Hertzian dipole, see what I am looking for is power radiated by the antenna, and that is given by half I naught square R rad. Okay. So I need two things here, I naught and R rad. Both the things are required here to solve. I naught and the value of R rad. Okay, I naught and the value of R rad. दोनों निकालना पड़ेगा मुझे यहाँ पे, ठीक है? दोनों निकालना पड़ेगा. Now, I naught is not given, but the strength of field is given. Case number 1, if it is Hertzian dipole of length lambda by 25. If it is Hertz dipole having the small length lambda by 25. अच्छा dear, what is the radiation resistance? पहले ये निकाल लें. Radiation resistance 80 pi square dl by lambda. Okay, just now also we solved a problem where length was lambda by 25. So this is 1.26 ohm. Okay, just like the previous question. Okay, but I naught कैसे आएगा? For I naught we'll have to use the mod h expression. For I naught we'll have to use the mod h expression. So what is going to be the mod h dear? Okay, what is the mod h? As I have already told you, it is given by beta I naught dl. Beta I naught dl sine theta divided by 4 pi r for Hertzian dipole. For the Hertzian dipole, right? Beta I naught dl sine theta divided by 4 pi r. I told you, sometimes इस expression पे question आएगा, तो इसको थोड़ा सा ध्यान रखना. Okay, for both. This one. अच्छा नहीं, ये तो आ गया Hertzian, ये तो हो गया lambda by 2 का. Where is the expression I had given to you? ये discuss किया था ना? हाँ, this one. Okay, I naught beta dl sine theta divided by 4 pi r. ठीक है? Okay, so using this we can calculate what is the value of I naught. So what is the H given to you? 5 microampere. 5 into 10 power minus 6, 5 microampere per meter is beta. अच्छा, beta कैसे आएगा now? देखो, what is the relation between beta and lambda? Beta is given by 2 pi by lambda. Beta is given by 2 pi by lambda. So I will use beta equal to 2 pi by lambda. Okay, current I naught निकालेंगे यहाँ से. Length is lambda by 25. So lambda will be cancelled. Sin theta at theta pi by 2 I require divided by 4 pi r, and r is 2 kilometer. The distance, that is 2 kilometer, already mentioned. 2 kilometer convert into meter, 2 into 10 power 3. Okay dear, solve from here and get what is the value of I naught. देखो lambda also got cancelled, so we don't need the value of lambda. तो इसको लिखा रहने देते हो for your later reference. Beta is 2 pi by lambda or omega by u. These two formulas of beta you should be always aware about. ठीक है? So now after the final calculation क्या आने वाला है? So 2 pi is cancelled. It's 0.5. Okay, please check out the calculation once. I am getting it as 0.5 ampere. Check I naught 0.5 ampere. ठीक है? अच्छा, अब अगर I naught 0.5 ampere आ गया है, so what is the value of radiated power? वो भी calculate कर लेते हैं ना. So what is the radiated power? That is half I naught square. I naught का value 0.5 square. I naught 0.5. Radiation resistance 1.26. Final answer dear. Final answer. Okay, 0.1575. 0.1575 watt. Or I can call it as 157.5 milliwatts. This is the power radiated by the under 157.5 milliwatt. Okay. Okay. हाँ, तो you can revise antenna here, ना? That's what. Praveen, ठीक है? चलो, next case, if it is a half wave dipole, so there at least we don't need to calculate the radiation resistance. Okay, next is lambda by 2 dipole. Next is the lambda by 2 dipole. So what is fixed is dear? What is fixed is you do need to calculate R rad. Like previous first part, we need to calculate R rad also. Here that is known to you, that is 73 ohms. And then, okay, mod h value, say, what is the mod h value? I told you that also. I naught cos pi by 2 cos theta is divided by 2 pi r sin theta. Okay, magnitude of the field is given as 5 microampere per meter. 5 into 10 power minus 6 is I naught cos of pi by 2 cos pi by 2, theta is pi by 2 upon 2 pi r is 2 kilometer, okay, sin pi by 2. So देखो, what is cos pi by 2? Cos pi by 2 0. Okay, then finally cos 0 will be 1. Okay, so ऊपर बचा I naught, denominator 2 pi into 2, 4 pi, 10 power 3, sin pi is pi 2 is equal to 1. So what is the value of I naught? 4 pi वहां shift कर देंगे तो you have 5. Okay, 4 pi and 10 power minus 3 is left. Okay, 0.0628. I naught is 0.0628 ampere, or I can call it as 62.8 milliampere. 62.8 milliampere. So what is the radiated power? Half I naught square, I naught का absolute value लिखा 0.0628 square into the radiation resistance, which is 73. Okay, which is 73. Okay. .144. What is the power that this one is radiating? Yeah, approximately milliwatt में लिखे तो 144 milliwatt. In terms of milliwatt, it is 144 milliwatts. Everybody clear? Check it out. Yeah, correct. Correct. Now, if this is 144 milliwatt, then guys, for the C part, now I don't have to do anything. For the C part, okay, for the C part, which is the monopole, which is the lambda by 4 monopole, the C part, which is lambda by 4 monopole, I can directly put the conclusion that the radiated power is nothing but half of 144. Because same current is supplied, same magnetic field means same current. Okay, so 72, half of the previous case, because the rest all the conditions are same. Divide by 2. Don't calculate it separately. If it is a fresh question, separately nikal lenge, but otherwise directly divide by 2. So half of the previous one. Everybody, half of the previous one. Okay, that's going to be half of the previous. Half of the previous. Next question now. Okay. Yeah, theta is pi by 2. Malvika, correct. Theta is pi by 2. A dipole with a length of 1.5 meter operates at 100 megahertz, while the other has a length of 15 meter and operates at 10 megahertz. The dipole are fed with the same current. What is the power radiated by two antenna will be? Choose the correct option. Choose the correct option. A dipole with a length of 1.5 meter operates at 100 megahertz, while the other has a length of 15 meter operates at 10 megahertz. The dipole are fed with the same current. What is the power radiated by the two antenna? What is the power radiated by the two antenna? What is the power that is radiated by the two antenna? देख लेते. चलो. Okay, a dipole with a length of 1.5 operates at 100. देखो, correspondingly दोनों के लिए lambda निकालेंगे. For frequency 100, lambda will be C by F. Okay, C is 3 into 10 power 8 and operating frequency is 100 megahertz. So lambda is 3. Okay, and length is 1.5. Length is 1.5 and that is lambda by 2 basically if you compare to this lambda. Okay. Now, another one has a length of 15, but that is at the frequency of 10. Okay, so correspondingly, the wavelength is 3 into 10 power 8 and frequency is 10 megahertz, 10 into 10 power 6. So this is 30 meter. Now, dear, look into it. The lambda is 30 meter and the other antenna has a length of 15 meter. Okay, that is also lambda by 2. That is also lambda by 2. Clear? Okay, this is L1, which is lambda 1 by 2. Okay, and this is L2, which is also correspondingly its lambda is lambda 2 by 2. So both are half wave dipole. Okay, and very important point is they are fed with the same current. They are fed with the same current. Okay, so basically here both are lambda by 2 dipoles. That means you have same R rad. Okay. Also, there is the same I naught. They are fed with the same current. So, will there be any difference in the radiation power? Fundamental question. The radiation power is half I naught square R. Okay, both are same. So, both antenna will be radiating the same power. Option number B. Option number B. Both antenna radiating the same power. Correct answer is option number B. Electric field measured in the far field of an antenna at a distance of 50 meter is 1 volt per meter. The average power densities at the distance of 500 meter from the antenna is how much? Again, a fundamental question, but yet important. Electric field measured in the far field of an antenna at a distance of 50 meter is 1 volt. What is the power density? Question is power density, but at a distance of 500 meter. My dear, field strength is given. Okay, field strength mod E, and in the far field it is proportional to 1 by R. If far field is not mentioned, then also by default assumed to be far field. All our discussions are in the far field only. Okay, so we know that mod E is proportional to 1 by R. Okay, so that means whatever is the first field strength divided by second field strength, because inversely related, so E1 upon E2 should be R2 upon R1, inverse. Yeah, iska inverse or ye iska inverse. Okay, so dear, what is going to be the second field strength? Mod of E2. Mod of E2. Mod of E2 will be R1 by R2 into mod E1. Okay, what is the first distance? 50. What is the second distance? 500. What is the first field? 1. So this is 50 by 500, 1 by 10, 0.1 volt per meter. 0.1 volt per meter. That is the mod E, 0.1 volt per meter. .1 volt per meter. ठीक है? That is the mod E. Clear everybody? Clear? Okay. Done है. बोल दो ना अरविंद को. उसके पास पैसे भी रखेंगे. Sorry for a disturbance. Hanji. Okay, so this is 0.1 volt per meter. We have got it. Now we have got the mod E. So what is the power density, Baba? What is the power density? That is very simple. Mod E square by 2 eta. Okay, use the formula. Okay, use the value 0.1 ka square divided by 2 eta. For free space eta is 120 pi. Write down the answer. That's it. Okay, so inverse relation. Okay, 1.3 to 10 power minus 5. So micro में convert करें तो 13.2. Basically 13.2 micro watt per square meter. 13.2 micro watt per square meter. (13.2 micro watt per square meter. Micro watt per square meter. Okay. Chalo. Any confusions up to this point, dear? Tell me. Any confusions up to this point? Tell me quickly. Hope it is clear. एक बार थोड़ा सा interactive हो जाओ. Come on, quickly tell me. Hope that is clear. So that now we proceed to another important discussion. So, you know, what I feel personally, dear, okay, I think today's idea is better. Okay, because if I had taken the complete EC syllabus marathon, So maybe how much time can I dedicate to antenna? 1.5 hours, because waveguide bhi discuss karna hai, transmission line, wave propagation, reflection, refraction, so many things. But here, more than 1.5. Okay, we are going in detail only in a sense, because abhi to और important चीजें start होनी है, so it will take time. So in detail we are discussing antenna. So I think that's good. Okay, if somebody wants to focus this topic, 100% you are able to focus on this session. Okay, चलते हैं next discussion की तरफ. Very important, that is the radiation patterns, or and simply known as the antenna pattern. Okay, now it is very clear to all of us that the electric field in the far zone is proportional to 1 by r. It is inversely proportional to r. Okay, if you move away from the source, okay, the power will decrease. As the wave propagates, power will decrease, no doubt. The strength of field and the power will decrease. Undoubtedly, we can't avoid that. Okay, but even if I take a fixed power, my idea is, देखो मेरा idea समझना पहले. Okay, my idea is कि suppose if I take the Hertzian dipole only once again, yeah, any dipole antenna if I take, okay, it is radiating some power in all direction, but does it radiate equally in all direction? Okay, is it radiating equally in all direction? Okay, the mod, agar hum hertz pe aa jaye wapas, if I come back to the Hertzian, what was the strength of the electric field? Okay, the mod E, okay, the mod E, mod E theta was eta multiplying by eta into beta I naught dl sine theta is divided by 4 pi r. We know that if I move away, okay, if I increase the distance, field will decrease. Like last question, the distance increased by 10 times, field decreased to 1/10. Pehle 1 volt per meter tha, then it became 0.1 volt per meter, like last question. And correspondingly, power density also reduced. But if I fix a particular distance, okay, if I fix a particular distance, okay, then still you are able to see that the mod E depends on the next thing, that is a sine theta, that is the direction. It depends on sine theta. Okay, it depends on what? It depends on theta as well. Say for example, थोड़ा सा पहले आपको एक बार हम क्विक रिवीजन देते जाएंगे. Okay, spherical coordinates, you have to jump back slightly into the spherical coordinates. And let me consider, say P is any point in the spherical coordinate, and that is represented as r theta phi. P is any point in the spherical coordinates represented as r theta phi. So dear, if I what shape has come? If I join this P with respect to center of the coordinate system, okay, the distance of the point P, okay, this distance of the point P is known as r. What is r theta phi mein? What is r? Spherical coordinates आप सभी ने पढ़ा होगा, but just a quick thing, because geometry is very important now what we are discussing into. The distance with respect to center, that is known as the r, radial distance. Okay, what is theta, what is phi? What is theta, what is phi? So theta is known as the co-latitude angle. Okay, here this vertical axis is z axis, this is my x axis, this is my y axis. Clear? Theta is known as the co-latitude angle, that is known as the angle subtended by the position vector OP. Angle subtended by the position vector OP with respect to the z axis. That is theta. Angle of the position. What is the position vector of a point? Okay, the line joining origin to the point P. The angle subtended with respect to z axis, that is known as the co-latitude angle. Okay, this is known as co-latitude. Angle of OP, okay, with respect to z axis. Angle of OP with respect to what? With respect to z axis. That is co-latitude. Okay, that is the co-latitude angle, theta. That is the theta coming in the formula. Okay, next. What is phi? Now, just drop this point. To explain you phi, what I will do is, drop this point on the xy plane. Just vertically, drop this point on the xy plane. Okay, let us consider this point, and suppose this point is P dash. The point which is dropped on the xy plane. Okay, join this point with respect to the origin. Okay, the angle of this OP dash with respect to x-axis, that is the azimuthal angle. That is the azimuthal angle. Why? Otherwise, आप इसको यहाँ से भी ले सकते हैं. What you can do is join this point vertically, perpendicularly. Sorry, vertically नहीं बोलूँगा. Join this point perpendicular with respect to z-axis. The angle of this line with respect to x-axis. तो ये x-axis के parallel एक line. This angle is the azimuthal angle. So idea is the point can be anywhere around the z-axis, na? The point can be anywhere around the z-axis. Okay, that location, okay, where it is around the z-axis, that circular direction around z-axis azimuthal, which is very same as cylindrical coordinate system. The phi coordinate is same as cylindrical coordinate system. Okay, to define it, we drop it in the xy plane. We call OP dash, phi is the angle of OP dash with respect to x-axis. With respect to the x-axis. ठीक है? अच्छा जी. Okay, so now what I'm telling is E is a function of sine theta. So let's take this particular picture here quickly. Suppose if I fix R, मैंने ये बोला ना, तो let me consider dear 2 points. Let us consider 2 points. Now one is P1, one is P2. Okay, such that both of these points have the same R. Okay, OP1, the length of OP1, the length of OP2, it is same as R. I want to fix the value of R. Okay, but both of the points have the different co-latitude, different inclination from the z-axis. Okay, one of them is theta, one of them is theta 2. And they are clearly not equal. They are clearly not equal. Although R for both is equal, both of them are equidistant. I have intentionally taken 2 points which are equal distance because we know that as a function of distance, we know that if you move away, the radiation will decrease. Okay, but even if I am in the same location, same distance, okay, will the radiation be equal everywhere or is it unequal? Definitely the mod E depends on theta, so it's not going to be equal everywhere. It is not going to be equal everywhere. Okay, so here and here, okay, when I take these 2 points, the strength of the field here will definitely not be equal to the strength of field here, and definitely the power radiated at these 2 places will also be different. Correspondingly, power density will change, radiated power will change. Okay, radiated power will change. So this also means that the power radiated at the first point and the power radiated at the 2 point, will it be equal? No. So the antenna basically radiates different power in different direction. What I can basically say is, there is different amount of radiation in different direction. Direction मतलब as decided by theta. So direction parameter को theta ले रहे हैं. Direction parameter is both theta and phi, but phi is not coming up here. Okay, direction can be decided by both theta and phi, but theta and phi is not coming up here. Idea is I'm only fixing R. Okay, but still mod E depends on theta. For some of the other antenna, it may depend on phi also. तो phi के respect में भी देखेंगे. Okay. So I hope first you get the concept that there is different amount of radiation in different direction, and I'm going to draw a radiation pattern, which is nothing. इसको simple language में समझेंगे. Radiation pattern, which is going to be the plot of E field. Okay, which is going to be the plot of E field. Okay, right. Or not only electric field, sometimes we may draw power also. Okay, it may be plot of the electric field or maybe plot of power. Okay, with respect to the direction coordinates are theta and phi for a fixed R. Okay, for a fixed R, we'll fix R and we'll try to trace the power and the electric field. दोनों के patterns देखेंगे अभी. Okay, so when the amplitude is plotted, mod E. Okay, when the amplitude of E field is plotted, that is known as the field pattern. That is going to be field pattern or simply the voltage pattern. But when the square of the amplitude, the square of the amplitude किस में आता है? Power density में. Mod E square comes in the power density. So when the square of the amplitude is plotted, we will be calling it as the power pattern. So दोनों की बात करेंगे अभी, field pattern and the power pattern. The field pattern and the power pattern. Okay, and why we need to discuss, I hope that idea is clear, because there is different radiation in the different direction. There is different radiation coming up in the different direction. ठीक है? Now, when we are going to plot the E field also, na, plotting it directly will be little complicated. So we break it into two parts. Okay, we break it into two parts. Okay, so three-dimensional plot of an antenna is avoided by plotting, is avoided directly, but we plot it separately. How separately? How separately? The normalized E field versus theta for a constant phi. So what we do, we assume that it may be a function of both theta and phi. So first we fix a phi. Okay, the plot of E versus theta for a constant phi will be known as E plane pattern or a vertical pattern. तो देखो यहाँ पे हमने किसको fix किया है? Constant phi. So let phi equal to 0. Any constant phi, na? Let's take phi equal to 0. So dear, in this picture, if I take phi equal to 0, can you tell me what particular plane it is going to correspond to? If you take phi equal to 0. If you take phi equal to 0. Okay. You're asking. Yeah, Manasvi, that's correct. Okay. Any other doubts I missed here? Correct. So if you take phi 0, the point P dash comes up here. But point P dash is just dropped here. Okay, phi is 0 at everywhere on the x-axis, na? Distance कुछ भी हो सकता है. Phi is 0 everywhere because angle is with x-axis. So everywhere on the x-axis, phi will be 0. Not only everywhere on x-axis, even if you're above x-axis, just above x-axis. If you just vertically above x-axis, if you're in any of this region, by point P अगर यहाँ होता है, then also you drop here and then you calculate phi, then also it is 0. So basically, if you take point anywhere, what is this now? This is x-axis and z-axis. Okay, if you take the point anywhere in the xz plane, okay, the phi will be 0. The phi equal to 0 is basically xz plane, which is vertical here. As per this picture, I can say it is a vertical plane, na? Okay, and for any constant phi, I have taken phi 0. If you take suppose phi equal to, ये मान लो 60 degree लिया आपने. Okay, suppose if this is 60 degree, then this is going to be the corresponding, but still it is vertical. It's like a vertical plate. Vertical plate anywhere around the z-axis. So when you fix up a value of phi, you get a vertical plane. Clear? You get a vertical plane. Okay, so when you are going to plot this, what I have told is the normalized E field, normalization करेंगे अभी, for a constant phi will be known as vertical pattern or E plane pattern. Okay, now the normalized E field versus phi for theta equal to pi by 2. Theta की fixed value given है pi by 2. The normalized field versus theta equal to pi by 2 will be the H plane pattern or the horizontal pattern. So dear, what is theta equal to pi by 2 now? Similarly, if you understand theta equal to pi by 2, तो देखो, theta is the measurement of angle with respect to z-axis. With respect to the z-axis. Clear everybody? With respect to the z-axis. Acha. Okay. So if I increase and make pi by 2. So 90 degree from z-axis, where do you come? 90 degree from z-axis, where do you come? Okay. 90 degree will be any point in the xy plane. यहाँ पे अगर आपने कोई भी point लिया, okay, that will be what is corresponding to 90 degree, na? Any point in the xy plane. Correct? Because any point on the xy plane, when you measure, when you start from z-axis तो perpendicular होता है, 90 degree आएगा. So, if you take up theta, which is pi by 2, that corresponds to xy plane here. As per this picture, it is xy plane and that is horizontal in nature. So, we call it as a horizontal plane pattern. Simply the horizontal pattern. Okay. Okay. Now normalization is of course done with respect to the maximum value. So how the normalization is done? Again, let's understand one of the cases with respect to Hertzian dipole. So what is the mod ES for the Hertzian dipole? Okay. What is the mod ES for the Hertzian dipole? It is given by eta I naught beta dl sin theta divided by 4 pi r. Okay, तो divide by 4 pi r यहाँ रख देते हैं. देखो dear, eta is constant. 120 pi, na, free space 120 pi. Current I naught, peak value of the current, that is given to you constant. Beta into dl constant. Okay, because for a particular antenna length to fix hoga na. Okay, For a particular antenna, all of this is fixed, and even I have fixed the value of R. We are drawing the pattern for fixed R. Okay, so under the discussions that we are having right now, all of this is fixed quantity. Okay, right now all of this is constant, and we can call it as A sine theta. Right now all of them is fixed because R is also fixed. Okay, so the E field function is A sine theta. What is the normalized E field? How do we normalize? I told you normalization is done with respect to maximum value of the mod ES. Now what is the maximum value of A sine theta is A? What is the maximum value of A sine theta is A? Okay, so what is the normalized ES? It is given by A sine theta by A, and that is known as sine theta. A sine theta by A, and that is known as the sine theta. Clear? That is known as sine theta. So what is the normalized field function? It is a very simple function, sine theta. अब इसको ध्यान से समझना. Okay, we call this normalized field function. It is a function of theta, na? So let this be f theta. Okay, let this normalized field function be f theta. That is sine theta. Okay, that is sine theta. Acha, if I explain you, okay, for a fixed theta, let us talk about the second parameter. H plane की बात करें पहले, horizontal pattern की बात करें. If I first talk about horizontal pattern, okay, theta equal to pi by 2 रखते हुए, okay, so horizontal pattern is plotted as theta equal to pi by 2. Okay, so what is f theta? Actually, it is only a function of theta only, and that is 1. F theta is 1, constant. Acha, f theta is representing what? It is representing the normalized value of the electric field in general. Okay, in general, the electric fields and magnetic fields we know are complex in nature. The phasor form of electric field is complex in nature because we have taken the magnitude, so that J part and all is gone away. But in general, this is complex number, and we are taking the magnitude of the complex number. Okay, we are taking the magnitude of the complex number. So this is just like mod of Z, mod of E, a mod of Z equal to 1. Ultimately, this represents mod E, na? So it's like mod of Z equal to 1. What is the plot you expect for mod Z equal to 1? What is the plot you expect for mod Z equal to 1? Okay, it's a unit circle basically. I will show you that plot, but thoda sa wait karenge. Okay, it's a unit circle basically. Okay, but when I talk about the vertical pattern, let me complete both the calculations. When I talk about the vertical pattern, okay, vertical pattern means phi equal to constant. Okay, we now take phi equal to constant, and as I told you, let's take phi 0. Okay, let's take the phi 0. Now, what is the f theta? That is the function of theta, that is sine theta. So here I will take different thetas and then I will explain you. Okay, here I will take the different thetas and then I will explain you the calculation. Okay, then I will explain you the calculation. So, okay, theta. Okay, let me make a table here. F theta. Okay, theta 0. Okay, what is f theta? Sine theta. Sine theta 0. Okay, suppose I take theta equal to 30 degree, pi by 6 ले लेते हैं, तो sin 30 degree 0.5. Okay, if I take 45 degree, pi by 4, sin pi by 4, 1 by root 2, 0.707. Okay, if I take suppose 60 degree, pi by 3, so root 3 by 2, 0.866. Directly value लिखते जा रहे हैं. If you take pi by 2, sin pi by 2 is 1. If you take then suppose 2 pi by 3, okay, again 0.866, root 3 by 2. Okay, if you take 3 pi by 4, okay, sin theta second quadrant में भी positive होता है. So if you take sin 3 pi by 4, again 1 by root 2, 0.707. Okay, finally if I take pi, because the range of co-latitude is 0 से pi, na? Okay, so if you finally take pi, sin pi is equal to 0. Okay, sin pi is equal to 0. As of now, these are the f theta values. Okay, later on I will add one more column here, but these are the f theta values. So definitely for different theta you will have different values. Okay, for different theta you will have different values, and f theta is mod E. It is representing mod E. Okay, so what is modulus of a complex number? Previous case it is fixed. Modulus of a complex number, dear, if this is the complex number, the modulus of any complex number is distance from origin, and it is fixed. Previous case it is fixed. Okay, so distance from origin is fixed. That is why it is tracing a circle. That is why it is tracing a circle, previous case mein. But here the distance is not fixed. Okay, here that distance is not fixed. Okay, so here when I try to draw, I'll show you the clear plots also. But here if I try to draw the plot, okay, for the theta equal to 0, it is 0. 0 distance means you are at origin. Mod z means distance from origin. Now next 0.5. Okay, for theta equal to pi by 6. So what do I do? First I have to take a line. Okay, which is theta equal to 30 degree. I take a line at 30 degree and at that line the magnitude is 0.5. Okay, 0.5. Okay, then I take another line 45 degree pe. Then I take another line 60 degree pe. Then I take another line 90 degree pe, etc, etc, etc. Okay, correspondingly theta I have to take. One of the magnitude was 0.5. Then I have got 0.707. Then I have got 0.866. Then I have got 1. Magnitude बढ़ते जा रहा है. Okay. Okay. I got this value, I got this value, I got this value, and I got this value. So when you are going to join it now, approximately, you get this shape. When you're going to join it now, approximately, and then let's continue the values. Okay, other values also, if you continue, okay, you will be getting something like this. Okay, similar pattern will be there in the left side also. Now have a look into the neat and clean plots here first. Have a look into this. Yeah, that's what I'm referring to. That's what I'm referring to. Okay, so this is your vertical pattern which is plotted in the XZ plane as I've just shown you this plot. Okay, similar part for other values of theta in the third and fourth quadrant. This will be obtained just to complete. Okay, just to complete. Okay, this is the unit circle, horizontal pattern. Okay, this is the horizontal pattern and this one is the vertical pattern. Both explained clearly. Okay, superposition of them. One is for fixed phi, one of them is for fixed theta. One of them is for fixed shift theta. When you superimpose them using graphical tools, I told you in a direct plot may be difficult. Direct plot would be difficult, sketching of it. But now when you superimpose using graphical tools, say you try to plot it using MATLAB, you get a donut type shape. You get shaped something like donut. Okay, so when the two plots are combined or superimposed, okay, the 3D plot that turns up is something of this type. That will be something of this nature. Okay, this is the radiation pattern for the Hertzian dipole. Okay. Now let's come to the power pattern also. Let's talk about more important parameter as finally what is important is the power pattern. Okay, so dear, power pattern. Now, as I told you, when the square of the amplitude is plotted. Okay, so what is the normalized amplitude? F theta. So what is going to be the normalized power function? F square theta. Normalized power function F square theta. So let's not repeat the table. यहीं पे entry कर देते हैं ना, dear. There itself, I have the F theta. So in this table itself, let me make the entry of F square theta, normalized power entry, that is sine square theta. So 0 square, 0.5 का square is 0.25, 1 by root 2 का square is 1 by 2, ये 0.5 होगा. Root 3 by 2 का square will be 3 by 4, that is 0.75. 1 square will be 1. This is again 0.75, reducing 0.5 and finally converges to 0. Acha dear, what you're going to feel is similar values will come up, a similar pattern will come up. Only thing is, isse difference kya aane wala hai? There will be a similar pattern, okay, but the values, because I've taken the square, all the values were less than 1, so when you take the square, they become even less than 1. So ye jo values hai na, ye aur small ho jayengi, okay, and the pattern would be little similar, but little bit pressed. Ek tarike se मान लो आपने press कर दिया है. It's going to be something like this. This will be representing the power. Okay, and this will be representing the field pattern. I will show this separately also. The trend is similar. It increases, maximizes at 1 at theta equal to 90 degree, again decreases, but all the values are reduced in amplitude. Okay, so this plot that is going to dive, even if you take a point by point value, it's like pressed version. Okay, it's like a pressed version of this. A very important point to be noted here itself is that this particular antenna, very clear now, it does not radiate. ये मैं आपको शुरुआत से ही बोल रहा हूं that it does not radiate equally in all directions. Yes or no? It does not radiate equally. In different directions, different radiated power. This is the power pattern, normalized power pattern. So there is a different radiation in the different power directions. Different radiation is there in the different direction. Okay. So when you talk about this value, this corresponds to the maxima. Okay, the maximum. अच्छा, because I have normalized the maximum value 1 ही आ सकता है, तो this is the maximum value, okay, which is obtained at theta equal to pi by 2. At theta equal to pi by 2. Okay, and this corresponds to no radiation at all. This corresponds to null. This also corresponds to null. At the extreme ends, at theta equal to 0 and pi, at the extreme ends, there is no radiation at all, and there is a radiation maximum which is in the perpendicular 90-degree direction. Perpendicular 90-degree direction. Perpendicular 90-degree direction. So let me first show you the power pattern as well. Power pattern plotted using f square theta, and this is what it is. Okay, इसको थोड़ा सा मैं यहाँ पे highlight कर देता हूँ. This is what. Okay, so that you visualize it clearly. This is what is going to be my power pattern. This has been plotted for phi equal to 0. This is the vertical pattern. Again, there are two cases here, vertical and horizontal. Vertical plane and horizontal plane mein to f theta was 1. So f square theta is again 1. No need to discuss it. Okay. That is not negative, Ananta. That is not negative. That is, you are plotting the modulus of a complex number, and distance from origin is the magnitude. Okay. So that is not going negative. The direction is changing. See, when I take this point, Ananta, it does not mean negative. Okay, the value is the distance from origin, because we have plotted, okay, modulus function, okay, and modulus represents distance from origin. So this much is the power obtained. What is the power distance from origin? Okay, negative में जाने का मतलब कि theta increase हो गया, theta increase हुआ. You are changing the theta basically. Okay, there is nothing like negative here. Okay, ji. Okay, ji. So this is what is the power pattern. This is what is the power pattern. Okay, unequal radiation. Okay, in different directions. Unequal radiation in the different direction. ठीक है. Now, इसको थोड़ा सा और discuss करेंगे detail में. Very, very important points coming up. Let me again highlight it a little bit more clearly. इसको देखेंगे. This is what is basically the power pattern of the antenna. Okay. What is the direction in which maxima is coming? What is the direction in which the maxima is coming? 90 degree. Already I told you. Okay. This is the maximum. This is the maximum. Okay. This is what is the maxima. So अब देखना. The story is something like. If you consider the Hertzian dipole, na. If you consider the Hertzian dipole, so what basically is happening here? इसकी axis को ले लेते हैं हम लोग. Okay, this is the Hertzian dipole. Okay, this is the Hertzian dipole. Now this corresponds to theta equal to 0 degree. This corresponds to theta equal to 180 degree. Theta equal to pi 180 degree. Both of them represents null points. Both of them represents null points. Okay. Now what is theta 90? ये z axis भी है. Okay. So theta 90. When you take 90 degree from the z axis, okay, you come in this special direction. Okay. This has the theta. मैं यहाँ पे लिख देता हूँ केवल. This is corresponding to theta, which is 90 degree. This is corresponding to the theta, which is 90 degree. And this is the direction of maxima. This is the direction of maximum radiation. This is the direction of maximum radiation. Okay. So, a Hertzian dipole, listen to the very important point now. A Hertzian dipole is radiating maximum. How? Along the perpendicular to its axis. Maximum radiation is obtained, okay, along perpendicular to the axis. Along perpendicular to the axis of the antenna. Such an antenna, proper definitions आगे लिखाऊंगा मैं आपको. Such an antenna which radiates maximum along perpendicular to the axis is known as broadside. Is known as broadside antenna. maximum radiation along perpendicular. Whenever an antenna radiates maximum perpendicular to its axis, such an antenna is known as broadside antenna. If an antenna radiates maximum along the ends, that will be end fire. That will be known as end fire. We'll see the definitions also later. अभी मैंने आपको roughly तो बता दिया है. This is what is the broadside antenna. This is what is the broadside antenna. Now, for any communication system also, when you are calculating the bandwidth, how do we define the bandwidth? How do we define the bandwidth? We define the bandwidth commonly as 3 dB bandwidth. We define the bandwidth commonly as a 3 dB bandwidth. Okay, that is known as half power bandwidth. Okay, and what is the idea for defining the bandwidth in the case of communication systems also? How do you define the bandwidth? Okay, the frequency up to which, if at least 50% of the power is also received of what was transmitted, okay, is acceptable. Okay, so the bandwidth, the frequency up to which you receive 50 or more than 50% of the power is known as the half power bandwidth. Okay, 3 dB bandwidth is known as the 3 dB bandwidth. Similar to the half power bandwidth, we define a term here, half power beamwidth, HPBW. This is known as half power या 3 dB beamwidth. Half power beamwidth. Okay, how it is defined? Let me write down. This is known as the angular separation between the half power points also known as the 3 dB points. This is known as the angular separation between because the pattern is plotted as a function of angle, as a function of theta. Okay, so angular separation between the half power points around the maxima. So maxima is at 90 degree. अब देखो, what is the maximum value of the normalized pattern? यहाँ पे आएंगे table पे वापस, that is 1. So where is the power half? Okay, at theta equal to 45 degree. Where is the power half again? At theta equal to 135. अगर degree में convert करें. Okay, so 135 and 45. Okay, 135 and 45. So the idea is, go back to the picture again. ये देखिए. Okay, when you take 45 degree angle, ये रहा, this one, the next important parameter. When you take this 45 degree angle, okay, this corresponds to the half power 3 dB point. Okay, half power, in short also known as the 3 dB point, because when you take in the log scale, okay, 10 log P naught by Pi, 10 log 1 by 2, that will be a reduction of 3 dB. Okay, and similarly 135 somewhere यहाँ आएगा, इसको हटा देते हैं. 135 यहाँ पे mention नहीं है, so let me draw that 135 line also. It should be somewhere between 120 and 135. This angle is known as 135. Okay, so this is also, this angle if you take up to this point, this is also 3 dB point. What is the angular separation between them? अब देखो, यहाँ पे इन लाइंस को फिर से बना देंगे हम लोग. Okay, let me draw these lines here again. Okay, 3 dB. Okay, this is the direction in which maximum radiation occur. Okay, when you go 45 degree this side, 3 dB reduction. When you go 45 degree this side, 3 dB reduction. When I combine both, this angular separation is known as the HPBW. Okay, this is known as the HPBW. And how much it is? It is corresponding to 135. This was 135 degree line. The above one was 45 degree line. And the HPBW is 90 degree. HPBW is also 90 degree. This is 90 degree. Standard value you can note down. For Hertzian dipole, it is 90 degree. The half power beam width for the Hertzian dipole is 90 degree. The half power beam width for the Hertzian dipole is known as the 90 degree. Clear, everybody? Okay, that is known as the 90 degree. HPBW is 90 degree. Okay. Okay. The HPBW is known as the 90 degree. Done. Okay. Now, one more role of the HPBW. See, when I say there is a, when I have defined the HPBW, one of the main intent of defining the HPBW, have a look into it once again. Okay, this is what is the HPBW. So any radiation occurring in it, we know that maximum is only in one direction. Okay, but any radiation such that the power is at least half of the maximum, okay, any such radiation will be known as the main beam of the antenna. This is what is known as now the main beam of the antenna. Okay, the main beam. What is the main beam of any antenna? It is the beam containing at least 50% of the maximum power. Okay, the beam containing at least 50% of the maximum power. Okay, the beam in which at least 50% of the maximum power, that is the main beam. That is the main beam. Major lobe bhi bolte hain, correct. Main beam or major lobe also, it's also known as, correct Ankit. Okay, so that is the concept of HPBW. Okay, then there is one more thing, FNBW. What is FNBW? FNBW is known as first null's beam width. First null's beam width. Okay, what is the beam width? Okay, that is angular separation, okay, between the two nulls around the maxima. Okay, this represents angular separation between the two null points. Angular separation, okay, between the two null points, and if there are multiple null points, we take the first null points around the maxima. The angular separation between the null points, the first null points around maxima. तो यहाँ पे कितना हुआ FNBW? यहाँ पे कितना हुआ FNBW? FNBW. So what is the first null point? Theta 0. This is the null point. This is also the null point. That is theta 180 degree. Okay. Theta 0 and theta 180 degree. So what are the nulls here? अगर हम again इसकी बात करें, that is the Hertzian. If I talk about the Hertzian, okay, so the null points are theta equal to 0 and 180 degree. So what is the FNBW? What is the angular separation between them? Is 180 degree. 180 degree. That is 180 degree. And that is twice of 90 degree. Achha, not only this, remember, in general, FNBW is twice of HPBW. It is twice of HPBW. FNBW is twice of HPBW. FNBW is always the twice of HPBW. Always twice of HPBW. Okay, like here it is twice of 45. Some more points to remember. Okay, like अगर मैं HPBW की बात करूँ, standard values. Okay, like Hertzian. These are values to remember. I mean, direct questions भी इस पे आता है. Hertzian, we got the HPBW as 90 degree. Okay, for lambda by 2 dipole, you will get it as 78 degree. You will get it as 78 degree. For lambda by 2 dipole, you will get it as 78 degree. You will get it as 78 degree. ठीक है. Now next, till now we have considered the radiation pattern. Okay, how is the antenna radiating in terms of diagram? Okay, in terms of power. Okay, in terms of power. Okay, in terms of the pictures. Now formulating it a little bit, radiation intensity की बात करेंगे. Okay, radiation intensity. I want to define a radiation intensity function. Okay, which is only a function of direction. So the simple idea is, guys, P average depends on mod E square. P average depends on mod E square, na? That means the power density of a wave will be proportional to 1 by r square, because mod E is proportional to 1 by r. Mod E square will be proportional to 1 by r square. This is going to be proportional to 1 by r square. So definitely when you take r square into P average, Okay, will it depend on r? When you multiply r square, it is only dependent on 1 by r square, so r ka factor fix ho jayega. This will be independent of r. And that is what the whole thing is. We are trying to study the relations, the patterns of the antenna in terms of direction, not in terms of the distance, because we know distance kam kuch nahi kar sakte. If you move away, the radiation will decrease. So this particular function r square p average will definitely become independent of r. Okay, and it will only be a function of theta. Okay, it will only be a function of, depends only on direction. Depends on direction. Now direction किससे define होता है? Theta or phi. Okay, direction is defined by theta or phi. So we call that particular function r square p average as u, radiation intensity. U theta phi as r square p average. R square p average. Okay. Also, the power radiated by the antenna is p average dot ds. Several times we have discussed. Now, what is the ds? P average is in the radial direction. P average pointing vector is always in the direction in which wave propagates, and wave is traveling in the radial direction everywhere around the antenna. Okay, so in the radial direction, spherical coordinate system mein ds is given by r square sin theta d phi. That is the value of ds. R square sin theta d phi. Agar vector form mein likhna hai. Okay, this is first the vector form only, p average dot ds, and in the vector form, ds along this direction, along the AR direction, is given by r square sin theta d phi AR. I put both of them, and then this particular function p average into r square will be the radiation intensity. Okay, so this becomes u theta phi. The term sin theta d phi will be known as the differential solid angle. Okay, so solid angle, a concept you study in physics. Okay, I don't think it's necessary to revise right now. Okay, I hope you know what solid angle is. ठीक है, अभी उस पे जाने का time नहीं है. Okay, because anyways I felt I am going a little bit slow and detail, and that's what always happens with the attendance. Nobody wants to, maximum don't wants to study for long hours, and then you expect कि सारे chapter का marathon करना है. See how the attendance is significantly going. Okay, so d omega is given by sin theta d phi, and that is the differential solid angle. That is known as the differential solid angle. That is known as steradians. Okay, the omega is known as the solid angle. Unit of solid angle is steradian. ठीक है, steradian. If you don't know about solid angle, you search on Google. आप पढ़ सकते हो. Very fundamental physics and mathematics term it is. Okay, and correspondingly the radiation intensity, because the radiated power is watt. Okay, this is in steradian, so this should be watt per steradian to get equal to the watt. So radiation intensity is defined in the form of watt per steradian. Okay, then we also define the average value of radiation intensity. Okay, and that turns out to be, after calculation, okay, p rad upon 4 pi, the average value of the radiation intensity. As I'm telling you, it's a function of direction. It will be different for different direction. Okay, so average value of it for all particular directions considered turns out to be p rad by 4 pi. Turns out to be p rad by 4 pi. Now next, directive gain. Okay, the directive gain. Okay, as I have clearly told you that this u, radiation intensity, okay, radiation intensity, okay, is a function of direction, and that decides how much is the antenna radiating in a particular direction. It is independent of distance now. Okay, higher the radiation in a particular direction, higher will be the value of u. Okay, so in a ratio form, when you compare the radiation intensity in any direction divided by what is the average value coming out, we call it as the gain in that particular direction. The gain of an antenna, directive gain of an antenna. Okay, directive gain means, of course, because it depends on direction, it is the radiation intensity of an antenna in that direction when divided by the overall, when divided by the average value of the radiation intensity that the antenna is having. Okay, the u upon u average, that is known as the directive gain. Okay, now this will have some important formulas. Lots of important questions are based on directive gain. इस पे बहुत question आते हैं. Okay, so directive gain, okay, which is also the ability of the antenna to direct radiated power in a given direction. See, how is the u theta in a particular direction high? When the antenna is radiating large amount of power in that direction. Okay, GD, as I told you, is simply u upon u average. Okay, but what is the formula for u? R square p average. Just now we discussed. What is u average? Average radiation intensity given by p rad by 4 pi. Right. So, in and all, I can say that the directive gain, this becomes an important formula. 4 pi r square p average. 4 pi r square p average is divided by p rad. is divided by P rad. 4 pi r square P average is divided by P rad. That is the directive gain. Okay, directive gain. 1 also, 2 also, anything can be there, Akansha. Okay, but most commonly 2. Okay. Sometimes it could be 3 also. See, it's not a subject, it's a chapter of a subject. But question बहुत frequently आता है, ठीक है, and you should attempt this chapter. Okay. चलो जी. That is the directive gain. 4 pi r square P average upon P rad. It depends on the antenna pattern clearly known. Okay. Achha, already we have seen for Hertzian dipole and same patterns. I have explained you with respect to Hertzian. Okay, but even for lambda by 2 dipole and lambda by 4 monopole, okay, the maxima will be at pi by 2. Okay, minima will be at 0 or pi by 2. And whenever an antenna radiating maximum at pi by 2, whenever an antenna radiating maximum perpendicular to the length, okay, that is broadside antenna. Okay, so Hertzian ले लो या lambda by 2 dipole or lambda by 4 monopole, all of them are Hertzian dipole category. Isotropic antenna, a concept I already told you. A one that radiates equally in all direction. Okay, a one that radiates equally in all direction, but this is just an ideal concept. Such an antenna do not really exist. Okay, isotropic antenna, one that radiates equally in all direction. If I just explain you roughly, already isotropic antenna mentioned in between. इसको देखना. Okay, so this is what is the pattern for Hertzian, right? This was the power pattern for Hertzian, and this is what isotropic mean. This is what isotropic mean. So for isotropic antenna, you take any angle, you take any direction. Okay. Okay. You take any angle, any direction. See, whether I take this direction, whether I start 0 degree also, whether I take 30 degree, whether I take 60 degree, whether I take 90 degree, what is the gain of this isotropic antenna? What is the gain of isotropic antenna? It is equal in all direction. Isn't it equal? It is equal in all direction. Are you getting it? It is equal in all the direction. But such is not the case for any other antenna. Suppose Hertzian. Okay, for Hertzian antenna, okay, if you take the gain in this direction, it is less. If you take the gain in this direction, more. If you take the gain at 90 degree, it is the highest. Okay, so in general, for most of the practical antenna, the gain depends on direction, but isotropic antenna is just an ideality where gain is equal in all direction. Such an antenna is an ideal antenna. Okay, and for such an antenna, GD will be 1. The directive gain is always 1. Why it is 1? Because the radiation intensity in every direction is same. So average value will, suppose radiation intensity in every direction is C. So average value भी C होगा ना, जब सब कुछ C है तो average भी C, तो C by C cancelled. So directive gain will be just equal to 1 in that case. Okay, for isotropic antenna. For isotropic antenna. Then we have the directivity concept. What is the directivity? Now we know that directive gain is a function of direction. The antenna can have different radiation in different direction, and hence it will have the directive gain which is different in different direction. But there will be one direction in which the gain is maximum. That maximum directive gain will be the directivity. That maximum directive gain is the directivity. It is the maximum directive gain in simple. Okay, in simple. Now directive gain is U upon U average. So directivity will be U max. What you have to maximize is U max because ये तो average value fix है. Okay, and that is known as the GD max. Directivity is the maximum value of the directive gain. Maximum value of the directive gain. ठीक है? ठीक है? हाँ. आकांक्षा देखो, IAC will not only make the questions. It is very clear IAC is only the conducting body. They will take care of the formality, but questions are invited from all IITs. The questions that you see, IAC as well as all 7 IITs will share the question. Of course, final choice of question remains with IAC. Okay, so paper, it's not that paper will be difficult, but yes, what Ankit Kumar is telling is correct. There are some questions, okay, the topics depend on them. So there's some questions you will see differently, but paper will be tough. It is a myth. It may be tough for IIT Roorkee also. Okay, so paper tough ho sakta hai, but especially IAC will make a tough paper. That is a myth. It may be tough at random. Okay, so don't count on that. Okay, don't count on that. ठीक है, चलिए. चलो, next parameter. Okay, ये हो गया डायरेक्टिव. चलो डायरेक्टिविटी कैलकुलेट. See, this is a very important area, GD. We will take the questions also in, but it is a very important area, GD. Now let's again pick up the Hertzian dipole to understand this, because questions इस पे solve करेंगे आगे हम. Let's take the Hertzian dipole case. For the Hertzian dipole case, I want to calculate the directive gain first of all. Let's start with GD, and that is U upon U average. Okay, acha, what is the U? U is given by R square P average. Okay, divided by U average, which is P rad upon 4 pi. Okay, now this becomes 4 pi R square. What is the P average? Okay, चलो अभी इसको P average ही रखते हैं. I'll substitute little later. But what is the P rad? How do you calculate radiated power? Radiated power is surface integral. It is known as the surface integral of the power density. And both if you take in the radial direction, so it is R square sin theta d theta d phi, as already explained. Okay, P average R square sin theta d theta d phi. D theta d phi, d theta मिस हो गया, d theta d phi, and double integral का साइन लगा देते हैं यहाँ पे. Okay, this is what it is. Now in numerator and denominator, okay, we both have average power. Okay, rather than putting the average power complete formula, average power mod e square by eta, then we know what is the mod e formula. But in the mod e there were some terms which were constant. How did I write down the formal final power? Okay, yeah, final mod e. Mod e was finally written as a sin theta. Some terms were fixed. Okay, some terms were fixed. So then we normalized. So even if you use the a sin theta, a and a will get cancelled, na? A and a will get cancelled. What is only going to be left is the sin theta function. So let us use the normalized value, na? Because P power is in both the expressions. So the fixed term, so the constant term will cancel. अगर कुछ constant है, if something is constant, that will be outside the integral, it will cancel with the numerator. So what I'm going to put here, okay, I will put the normalized value. Okay, here, put the normalized value, because you have it both in the numerator, denominator. So when you put the normalized power value, normalized field value was sin theta, normalized power value was sin square theta. याद होना चाहिए आपको, that was sin square theta. So I am going to be left with 4 pi r square sin square theta, 4 pi r square sin square theta divided by double integral, again sin square theta. Acha, by the way, integration is with respect to theta and phi. Hey, what is r doing inside? With respect to theta phi, r constant है ना, तो चलो यहीं से r outside, r square, then I have double integral sin square theta, and then further sin theta d phi. Okay, so what is the GD turning out to be? So dear, r square cancel कर दें, so I have 4 pi sin square theta. 4 pi sin square theta is divided by the double integral of sin cube theta d theta d phi. Now limits, okay, d theta, theta is 0 से pi, complete range of azimuth, co-latitude is 0 से pi, complete range of azimuthal angle 0 से 2 pi. ठीक है, we can separate the denominator integration, so this becomes 4 pi sin square theta divided by integral d phi separate कर देते, variables are separable, integral d phi 0 से 2 pi, integral sin cube theta 0 से pi, sin cube theta d theta. Now this is further equal to 4 pi sin square theta divided by d phi. d phi का integral phi upper minus lower limit आ गया 2 pi. Okay, sin cube theta का integral, dear, please integrate yourself. I'm not spending time on integration. I'm using Wallis formula. Hint मैं बोल दे रहा हूँ. I'm using the Wallis formula to integrate. First convert it twice 0 से pi by 2, and then 3 minus 1 2 है, and denominator में 3 into 1, odd value है तो k will be 1. Okay, so 2 pi cancel. Okay, ये 2 pi 4 हो गया. Actually the 4 pi itself will cancel. 2 by 3 going above, it's 3 by 2 sin square theta. That is 1.5 sin square theta. Okay. Acha, this is the GD. For a Hertzian dipole, the GD is 1.5 sin square theta. So what is the directivity, dear? Maximum value of the directive gain. Maximum value is 1. Sin square theta ka maximum value 1. So the maximum overall value 1.5. So what is the directivity of Hertzian dipole? 1.5. This is how we calculate. So I think, yeah, this is what is available for you. Okay, look into this. Hertzian dipole, dear. For Hertzian dipole, the directive gain turned out to be 1.5 sine square theta with the directivity 1.5. This value, these constants are important. Sometimes direct question aa jata hai is pe. Okay, at least one marker. Not in gate. Such direct question not in gate, but maybe in ECE or ISRO or BARC examinations, sometimes directly radiation resistance or directivity values, ye sare constants pooch liye jate hain. Okay. So then for lambda by 2 dipole, when you solve, you are going to get the directivity 1.64. For Hertzian monopole, it's going to be 3, double of this. For lambda by 4 monopole, this is again double of it. You know why double? Why double? Why it doubles? Why the directivity doubles? Why the directivity doubles for monopole? My simple reason is not only directivity, directive gain basically will double. This function will come up as 3 sine square theta. The reason is, what is the GD? Final formula that has come up is 4 pi u divided by p rad. U upon u average hota hai p rad by 4 pi. So basically in the monopole what happened, the radiated power becomes half, na? This depends on the MODI. This is the radiation pattern. That depends on MODI. MODI is same. The expression of field is same for both the antennas, dipole or monopole. But what changed was power and it became half. So if denominator is half, overall quantity doubles, na? Overall quantity doubles. Okay. So this is into 2. I'll write down the reason. Because radiated power is half. Radiation power half हो जाता है, इसलिए directivity और directive gains both will double here. Both will double. चलो. So yeah, just a few more concepts and then we jump to the question, dear. फिर question पे jump करते हैं. ठीक है. Let me see, guys, how many of you are active and alive. Come on, guys. I want to see all the active persons in the comment box. I want to see all the active persons in the comment box. Come on, everybody. This much on time, detailed time on one chapter you are getting means your antenna is complete. Your activeness will show me how much you are eager. I want to see all the active guys in the comment box right now. Come on. Come on, let's boost up the energy. Come on, everybody. Okay, power gain. Okay, power gain. Already in the beginning, I told you that whatever is the power that you input to the antenna, ये हम लोग beginning में discuss कर चुके हैं. Whatever is the power that you input to the antenna, okay, a part of it is radiated, and some part of it is lost due to the conductors, okay, which are building the antenna, known as the ohmic losses, okay, so P in is PL plus P rad, okay, P in is PL plus P rad, and P is half I square R. Okay, so writing the power, radiated power already written, half I square R rad. I am writing the lost power. The power is lost due to conductors, but suppose again that lost power was dissipated in a fictitious resistance. What is the value of the resistance which will dissipate same power as what is lost in the conductor? Suppose that is RL, and that is known as the loss resistance of the antenna. Like radiation resistance, we have another concept that is known as the loss resistance of the antenna, and then the radiation efficiency, guys, already was defined. पहले उस पे आ जाते हैं. You remember this was already defined. Okay, this was already defined. Radiation resistance P rad upon P in. Okay, or P in was PL upon P rad, and then it is R rad. P is half I square R, half I square cancel throughout. It is R rad upon R rad plus RL. ये आता है, इस पे भी question आता है. So radiation efficiency is R rad upon R rad plus RL, या simply P rad upon P in, या it is also equivalent to GP upon GD. Now where GD already discussed, GD was known as the directive gain. The term GP here is known as the power gain. The term GP here is known as the power gain, which is also defined as 4 pi U upon input power. Okay. 4 pi U upon the power that is input to the antenna. Okay. Upon the power that is input to the antenna. Okay. Right. In a sense, what is the difference between directive gain and power gain? Dekho, there is an antenna. In a particular direction, agar Hertzian kahi le, in a particular direction it is radiating the maximum direction. In other directions it is radiating differently. Okay, there will be some radiation in this direction, less than the maxima definitely. The radiation in this direction as compared with the maxima, okay, was the directive. There we talk about the directive gain. But power gain means the direction, the radiation in a particular direction as compared to the input power itself, as compared to what is the power input to the antenna. Okay, that is how we normally consider the power gain. That is the, somehow you can understand the difference between directive gain and the power gain. Okay, in the directive gain, what was coming up here is P rad. Okay, in the power gain, it is P in. It is P in. Okay, so these are the formulas. GP upon GD is also the radiation intensity, and that is P rad upon P in. This is what is the basic. When I talk about efficiency, there are two cases: radiation efficiency and radiation efficiency and aperture efficiency. Aperture efficiency की बात भी करेंगे आगे. We'll talk about aperture efficiency also. So let me complete that part also. Then we'll jump to the question. Aperture efficiency. To define the aperture efficiency, first I need to define what is known as the effective area of antenna. What is known as the effective area of antenna? Okay. What is known as effective area of antenna? Okay. Now, if we specially talk with respect to a receiving antenna, this concept is mostly with respect to receiving antenna. This is mostly with respect to receiving antenna. So, dekho, with respect to receiving antenna. So, suppose that, this is some antenna. Let's assume one case. Okay, this is some receiving antenna. Okay, and some power, some electromagnetic power is going to fall upon it and it captures that electromagnetic power. Okay, so there is some wave that is traveling across it. Okay, there is some EM wave that is traveling across it. Okay, now once it falls over it, what is the power received by it? What is the power received by it? It is given by the average power density. The power density of the wave. So let's say the wave that is traveling has the power density as P average. Okay, dot ds. But what is the case you see here is, what is the first case you see here is, dear? What is the first case you see here is that the P average is actually perpendicular to the surface. Okay, the wave is traveling such that it falls normally to the receiving surface. The wave is traveling such that it falls normally to the receiving surface. Okay, normally to the receiving surface. And that is why I can say that, what? Okay, what is the direction of ds? Direction of any surface is also normal to it. Direction of P average is also normal to the given receiving antenna. So both are in the same direction. Okay, two vectors in the same direction. A dot B is known as AB. If two vectors are in same direction, A dot B is known as AB, na? Because cos 0 ka case aayega. Cos 0 is 1. So A dot B is known as AB. Now P average is the power density of the wave that is incident on the receiver. Power density of the wave which has been transmitted by some other transmitter. This is the power density of the wave which has been transmitted by some other transmitter. It has nothing to do with the surface area of this. I mean, it's not a function of this ds. And if it is independent of ds, because ये तो किसी और transmitter की वजह से आ रहा है. If it is independent of the ds, if it is constant with respect to ds, okay, if it is constant with respect to ds, we take it outside and then we are left with integral ds. And guys, as per the basic laws, integral ds is known as the surface area. So dear, what is the PR? Okay. What is the PR? It is the power density that falls on the receiver multiplied by the surface area of the receiver. This is what is the power received by the antenna. Received power की बात कर रहे हैं. ठीक है. But the case that I have taken is that P average is normal to the receiver surface. If it is normal to the receiver surface, but it may not be generally true. Now say this is the receiver, maybe a parabolic receiver, okay, and the wave that is incident over it, okay, may not be normal always. So this is not normal. Okay, at some points it may strike normally, okay, but in general it may not be normal. It may be coming, it may be traveling. Waves travel in all direction. Okay, so it may not be always normal. Okay, it can be in any random direction also. Okay, it can be in any random direction also. Okay, so if it is not normal, okay, then then the PR will definitely not be equal to this quantity. See, this is A dot B. A dot B maximum value AB at theta equal to 0. When is the dot product maximum? When the theta is 0. But now theta will be non-zero. Now the theta will be non-zero. This was the maximum value of A dot B, but now the dot product itself is not maximized. The power that is now going to be received is definitely less than what I have written earlier. Okay, because A dot B here will not be equal to AB. It is actually less than AB because of cos theta less than 1. Cos theta ka maximum value 1 hota hai. 0 bhi nahi hoga, but it is less than the previous case. It is less than the previous case. Okay. In such cases, we define the concept of effective area of antenna. We define the concept of effective area of antenna. We say that the power received, whatever has come up, we say that the received power of the antenna, whatever has been calculated, is equivalent to the power density multiplied by the area which is known as the effective area, not the actual physical area, but known as the effective area of the antenna. It is known as the effective area of an antenna, and it is defined. Okay, it is defined as a very important property of receiving antenna, because it is very evident from the relation that if the effective area of a receiving antenna is more, it will be able to capture more power. It will be able to receive more power through electromagnetic energy which is falling on it. Okay, so here when I called S, this is the actual physical area. Here this is known as the effective area. Effective area. Yeah, in a context, Ankit, you can also call it as the useful area. So that is the concept of effective area, important for receiving antenna discussion. Okay, and it is the ratio of, now what is effective area? It is the PR upon P average basically. It is the PR upon P average. Ye dekh lenge na? Okay, so this effective area, PR upon P average, is known as the ratio of the time average power received to the time average power of the incident wave. Okay, power density of the incident wave divided by the power that has been captured by the antenna, the ratio of them is effective area, and it is a very important parameter because it is telling the measure of the ability of the antenna to extract how much energy it can extract from a passing electromagnetic wave. Okay, after solving through several Thevenin network calculation, the final formulas ki baat karte hain, how it turns out, not deriving it up, but effective area in general. Okay, we make the equivalent Thevenin equivalent of the network at the receiving side, antenna at the receiving side, and we get the answer AE is lambda square by 4 pi into GD. Okay, or sometimes we also refer what is the maximum effective area. Maximum effective area will be GD max. It depends on GD, na? So to maximize the effective area, you should have GD max, and GD max is known as directivity. That is also one of the case. Maximum effective area is lambda square by 4 pi GD. Okay. So say for example, if I take a Hertzian dipole, what is the maximum effective area for Hertzian dipole? Lambda square by 4 pi into directivity. Directivity is 1.5. What was directivity? 1.5. Now a lambda can be given and you can calculate these values. Take any lambda can be given and you can calculate. Okay. Then the next Friis transmission equation, okay, Friis transmission equation, which gives the relation between how much power is transmitted by a transmitter, out of which how much power is received by the receiver. Okay, received by the receiver. Okay. So we have suppose two antennas which are separated by a distance r. Okay, and they both should be in the far zone of each other because we are only discussing far field equation. The transmitter has the effective area AE, which is not required. The effective area is important for receiving, but let me specify it as effective area AET. The PT, it has the power transmitted PT. Okay, the important points here is PT and GDT. Directive gain of the transmitting antenna, GDT. Okay, PT is nothing but the P rad. Abhi tak P rad bol rahe the na. Whatever is the power transmitted by the transmitter, I am calling it as PT. Simply P rad. Okay, it is at a distance r from a receiver. Receiver has effective area AER. That is important. It has the power that is received. Suppose that is PR. That is what I want to calculate. And it has the directive gain GD, which will be known as GDR. Okay, and PR. That is what I want to calculate. Okay. If both of them are in the far zone of each other, the received power after calculation turns out to be GDR GDT, product of both the directive gains. It turns out to be GDR GDT into lambda by 4 pi r whole square into PT. GDR GDT into lambda by 4 pi r whole square into PT. GDR into GDT into lambda by 4 pi r whole square into PT. Okay. That is what this formula is known as the Friis transmission equation. Known as what? Known as the Friis transmission equation. Okay. Known as the Friis transmission equation. Acha, there is also one more term that I will define. Okay, like we defined eta r, that is eta a, and that is known as efficiency in terms of aperture. Aperture efficiency. What is aperture efficiency of an antenna? And it is equal to the effective area of the antenna, okay, when compared with the physical area of the antenna. Okay, that is the, like radiation efficiency, we have another term, aperture efficiency, effective area upon the physical area, the ratio of these two, that is the aperture efficiency. Aperture efficiency. Okay. Okay. So before I take a question, let me remind you once, guys. Don't forget, Saturday we are starting the maths revision. Saturday and Sunday, 2 days, 10 a.m. we are starting with the maths revision. Okay, so I've already told you multiple times. Okay, Saturday we are finally starting, and some variety of questions. Now let us see. Already some questions we have discussed. Now another question. Okay. Of course, yeah, you know, if you want to mention in the log scale, it will be 10 log because they are power gains. Okay. So as I just explained, Anantana, dekho, power efficiency nahi, basically radiation efficiency, but yeah, it is the power radiated by the antenna as compared to what is input to it. In terms of power gain, which is again a function of direction, you see, we are trying to see in a particular direction, there is some power radiated by the antenna. Okay, what is that power when you compare to what is the power input to the antenna? Okay, so that is a directional property. Chalo. Come here. An antenna has a radiation resistance of, they are related. Okay, they are related by the GD parameter also. So an antenna has a radiation resistance of 72, loss resistance of 8, and power gain of 16. Calculate the directivity. Okay, basically calculate the directive gain. It should be. यहाँ पे by default maximize नहीं होगा. So let me write it as calculate the directive gain basically. Okay. So देखो, power gain is given in directive gain. So question can be based on aperture efficiency. Okay. Okay. Sorry, aperture बोल दिया मैंने, radiation efficiency. Radiation efficiency, GP upon GD. Okay. It is also known as Prad upon Pin. Prad upon Pin. It is also known as, three important cases. It is also known as Rad upon Rad plus RL. Correct. Okay. So what is the efficiency? The efficiency given nahi hai, but power gain given hai 16. Okay. It's absolute value 16. Divide by GD. That is equal to radiation resistance given as 72 upon 72 plus loss resistance. Okay. So just we have to equate these two and we get the value of GD. Simple one. Okay, 72 plus 8, that is 16 into 80 is divided by 72. See what is the answer turning up? See, you are telling 17.8. Let's take it as 17.8 as per what you are telling. I trust your calculation, 17.8. Let's take it as the 17.8. Done? Can you tell me this value first? An antenna has its E field given as E naught sine 2 theta. What is the HPBW? Half power beam width. Angular separation between the 3 dB points around the maxima. Okay. Around the maxima. around the maxima. अब देखो 3 dB points around the maxima, we need half power points basically. We need half power. These half power points are also known as 3 dB points. Okay, so those are the points where power is half of the maximum power. Okay, acha. For the power to be maximized, what is going to be the direction? Sin 2 theta is maximum as, ye dekho, this is maximum at, देखो actually what is maximum is 990, तो यहाँ पे 90 रखने के लिए 2 theta will be 90. Okay, so here the power will be maximized at 45 degrees. Some random function can be given and they're asking the HPVW. Okay, so the maximum power will be achieved at 45 degree. Okay, now we want those points. Okay, we want those points at which power is half, reduced to half. But dear, simple, power is proportional to, okay, power is proportional to square of the amplitude. Okay, square of the amplitude. Okay, so if the power is half, okay, that means I can say that mod E square is half. So what is mod E? Okay, what is mod E? So basically I can say that whenever E is given, we need those points where mod E square becomes half. The mod E will be 1 by root 2 basically. Mod E becomes 1 by root 2, the mod E max value. Okay. So mod E, what is the magnitude? E naught sin 2 theta. Okay, that should be 1 by root 2 times the mod E max. And what is the mod E max value? My max value will be E naught because sin theta, sin whatever it is, sin value is maximum 1. So overall maximum of this electric field will be E naught. E naught cancelled. Okay, E naught cancelled. You have sin 2 theta equal to 1 by root 2. Now 1 by root 2 is how much? 1 by root 2 is basically sin 45 degree, or second quadrant में भी sin positive होता है, sin 135 degree. So here 2 theta is 45 degree or 135 degree. Okay, so your 3 dB points are theta equal to 22.5 degree, or half of this कितना हो जाएगा? 67.5 degree. Correct है? Yes, correct है. Right. So what is HPBW? Half power beam width. It is the angular separation between these 2 points. These are both the points where power becomes half. Okay, so angular separation between these 2 points, that is 67.5 minus 22.5. Okay, the angular separation is 45 degree or pi by 4. Pi by 4, correct answer is B. HPBW. HPBW. ठीक है. Acha, if they ask, tell me FNBW, first null beam width, you can calculate that also, but it is always twice of HPBW. By first null beam width, for that you need the null points. You can calculate null also, but not required, na? 2 into 45, 90 degree kar dijiye directly. If the question is FNBW, pi by 2 will be the answer then. Okay, pi by 2 will be the answer for FNBW. Okay, but here it was HPBW. Okay, done hai, ho gaya. Next question. An antenna with the efficiency of 90 degree has a maximum radiation intensity of 0.5 watt per steradian. Calculate the directivity of the antenna when the input power to the antenna is 0.4. When the input power to the antenna is 0.4. An antenna with the efficiency of 90% has a maximum radiation intensity of 0.5 watt per steradian. Okay, calculate the directivity of the antenna. Okay, when the input power to the antenna is 0.4. Tell me. Again, यार यहाँ पे देखो, in general it should not be directivity. Let me again, in general call it as directive gain. That is the proper thing. नहीं, maximum radiation intensity given है. Correct है, correct है. Directivity है, maximum radiation intensity है. ठीक है. So now देखो, what I need to find out? I need directivity. Dear, directivity is known as GD max. Acha, what is the GD formula? GD formula was U upon U average. So GD max formula is U max upon U average. That is why U max is given. Maximum radiation intensity. Acha, what is U max? 0.5. ये given है. Divided by, what is the average radiation intensity formula, dear? P rad upon 4 pi. Okay, so what is the directivity now? 4 pi को ऊपर ले देंगे. 4 pi into 0.5. 2 pi divided by P rad. Now, how do you calculate P rad? For that, efficiency is given. For that efficiency normally means radiation efficiency is 0.9, and that is equivalent to P rad upon P in. Okay, the power that is input to the antenna is given 0.4. The question solved, na? Power that is input to the antenna is given to you. So what is the power radiated? 0.9, 90% of what is input to the antenna. So that becomes 0.36. Okay, so my answer is 2 pi divided by 0.36. Let's turn out what is the answer coming up. 17.45. It is equivalent to 17.45. Option number B, approximately. Correct? It is 17.45. Okay. Chalo. Next question. Next one. Again, one more important question. Don't spam here, Alam. Okay. The electric field intensity at a distance of 10 km from an antenna having a directive gain of 5 dB and radiating a total power of 20. Directive gain se start karenge. Directive gain is, it is given in decibel. What does it mean? It is 10 log GD. I told you to take 10 log. Okay, whenever power calculations are involved. इसको तो पहले block करते हैं. Okay, let me remove it. Just a second, guys. Complete this question. Complete this question. Okay, so we have 10 log GD equal to 5. Okay, we have 10 log GD equal to 5. GD will be 10 raised to the power 5 by 10. Okay, that's like root 10, so 3.16. So that is the absolute value of GD. Okay, now let us start with the GD formula. Okay, let us start with the GD formula. GD, once again dear, yahi se start karenge. U upon U average. U is R square P average. U average value is P rad by 4 pi. You know, such questions normally are 2-marker question, but they are very simple now. सारा कुछ आपने पढ़ लिया है. Very simple it is now. 4 by R square P average upon P rad. Okay, so what is the GD? 3.16. देखो क्या क्या given है इसमें से. GD is known to me. 4 pi R square. R is the distance at which I am calculating. So we are right now calculating at a distance of 10 km. So R is 10 into 10 raised to the power 3. So R is 10 ki power 4. And it is radiating a total power. What is given to you? Radiated power 20 kilowatt. 20 into 10 raised to the power 3. Okay. Chalo. So let's put down these values. So R is 10 power 4. Further square. P average we can calculate from here. Power density divided by radiated power 20 kilowatt, 20 into 10 power 3. So यहाँ से आप निकाल लेंगे P average. P average will also be mod E square by 2 eta. So what is P average first of all? So यहाँ से mod E निकाल लेंगे because eventually what I need is the field intensity. Okay, what is the mod E? Okay, ठीक है, तो उसके लिए पहले P average आ गया. तो let's complete this calculation, guys. 5 into 5.029, 10 power minus 3. 5.03 approximately 10 power minus 3 or minus 5. 10 power minus 5, clear? Now put down the value of eta. Okay, what is going to be mod E? Mod E, okay, this value 5.03 10 power minus 5 into 2 eta. Eta for free space 120 pi and mod E will be under root of this term. Under root of this term. Okay. 0.195 approximately. Okay. 0.195 volt per meter. Okay जी, 0.195 volt per meter. Done. Important 2 marker category questions है ये. But it is very simple. See, antenna can also be, handled. Okay. Provided there's a thorough study that you have done. ठीक है, thorough study that you have done. चलो. Quickly, next one चलेंगे. An antenna designed to operate at a frequency of 40 megahertz whose quality factor. Chalo. One more thing. What is the quality factor of an antenna? It is given by operating frequency divided by the bandwidth. The bandwidth of the antenna is how much? You can note down this one more formula. Okay, so what is the bandwidth? बहुत ज़्यादा इस पे question नहीं आते, but you should just know at least. Okay, so bandwidth here will be operating frequency divided by the given quality factor. Operating frequency 40 megahertz divided by the quality factor is 50. Okay, so in terms of kilohertz given है तो 0.8 10 power 3 करेंगे separate. 800 kilohertz is my answer. 800 kilohertz answer number B. ठीक है. Next question. हाँ, now this is important one. यहाँ पे sometimes students are stuck, so let's take this important case. The radiation intensity of an antenna is given as U 2 sin theta sin phi in the range 0 less than theta less than pi, 0 less than phi less than pi, and 0 elsewhere. What is the directivity of such an antenna? Important. This is little calculative, so this also 2 marker expected question. बताइए. Just a second, है ना? Just a second. Start some basic calculations by the time. Okay. So guys, 3 hours almost. थोड़ा सा late start किया था आज, but 3 hours almost non-stop, and it's a single session of antenna. Doesn't make sense to give a break. Doesn't make sense to give a break here. Okay, but do let me know around few more questions abhi. But after few more questions, do you want me to start antenna array also? Do you want me to start antenna array? But I will not give a break. जो होगा continuity में होगा. Okay. So you let me know, do you want me to continue antenna array also? But we cannot afford a break at this time for a single session at least. I am ready to go non-stop. Okay. I am also slight hungry, but no problem. I am ready to go. But break will spoil the rhythm of a chapter. The radiation intensity is given to you. देखो directivity के लिए सबसे पहले तो we know that directivity is GD max. Directivity is known as the GD max. Okay, so first let us work on the GD. GD. Once again, U upon U average. Okay, U is given to us this time. So you don't write R square P average. U is directly given. Okay, so what is U average? P rad upon 4 pi. Okay, so we have 4 pi into U. U is 2 sin theta sin phi. Okay, in the given range, of course. Okay, divided by P rad. So, the main point of the question is solving for P rad. The main point is solving for the P rad. Okay, P rad solve करेंगे. Okay, so to complete the GD, I need P rad. Now, how do I calculate P rad? P rad is P average dot ds. P average R square sin theta d theta d phi. सारे formula revise कर लेना एक बार because we have done several formulas here. Okay, so now this particular parameter again is the radiation intensity R square P average, and that is given to me. Okay, so the P rad, okay, d theta d phi double integral के form में है, is double integral of U. What is the U? Is 2 sin theta sin phi, correct? 2 sin theta sin phi. Okay. Okay, into sin theta further, into d theta, into d phi. Okay, let's separate the variables basically. Let us separate the variable basically. Sin square theta हो जाएगा, 2 को अलग कर देते हैं. So one of the function is sin square theta d theta. Okay, integral theta equal to 0 से pi. Another function, there is a phi function also. Okay, sin phi d phi. Okay, from phi equal to 0 से I think phi का range भी complete नहीं है, phi है, phi is up to pi only. Okay, ठीक है. So now this is equal to twice. Let me solve it. Integration I solve my own way. You can solve later on also. Twice पहले इंटीग्रल 0 से pi by 2 किया, sin square theta तो 1 upon 2, even power है pi by 2. This is the first integral answer. Multiplied by sin phi. Sin phi को तो directly you can like write down cos phi. This is going to give you as only 2 will be the answer. Minus cos phi and cos phi minus or minus 1. Yeah, that's going to be 2. Okay, just check out the calculation once. Okay, 2 2s are cancelled with 4. So this answer is 2 pi. Integration I hope you can handle. ठीक है, बाद में कर लेना integration. Okay, that's what. If you by chance know na Wallis, I've taught you Wallis in maths. I've separate videos on that. When you know Wallis in practice na, see I did not remember the formula. Immediately I apply Wallis. Similarly, जो Hertzian का directivity निकाल रहे थे, there also I applied Wallis immediately. I don't remember any answer. So very helpful Wallis integral formula is. Instantly you can calculate. जितने मैं बोला उतने में आप निकाल लेते. चलो ठीक है. So it should be 2 pi. So now we are done now. What is the GD dear? What is the GD? It was 4 pi into u 2 sin theta sin phi divided by radiated power, which turns out to be 2 pi. So the GD as a function of theta phi, final answer, okay, it's 2 sin theta sin phi. Sorry, 2 nahi, 4 hoga. It is going to be 4 sin theta sin phi. Okay, for what values? ये भी mention कर देते. 0 less than equal to theta less than equal to pi. 0 less than equal to phi less than equal to pi. This calls for a very important question and its solution. So sometimes they can ask you the expression of GD. ये भी याद रखना. Sometimes they can ask you the expression for GD. Sometimes they can ask you the expression for GD. Okay, that is also one question. Now they have asked the directivity. ठीक है, तो directivity निकालेंगे. GD max 4 sin theta max value 1. You only have to see sin theta is maximum at pi by 2. Is the pi by 2 in the range? Yes. Sin phi also maximum at pi by 2. Pi by 2 in the range of phi? Yes. So maximum value is 1 into 1 for both. So it is 4 in dB. Okay, अगर dB में बोला है तो answer will be 10 log of 4. 10 log 4 becomes 20 log 2. 6 dB होना चाहिए ये. 6 dB. Answer is B. So can you handle these questions now? See yourself. Internally you analyze. I'm not asking you to comment, but internally analyze. कि, you know, if you are able to handle these questions means you're becoming comfortable in antenna. अगर नहीं हो रहा है तो comment करो अगर कोई doubt है. If you are able to handle, fine. Stay silent. I know. But in case any doubts or anywhere you're stucking, some step is disturbing you, then you can let me know. Acha ji. If this is clear na, if this is clear, I will give you one question here as homework. And I think it's not mentioned here. It has missed. I'll write down. Dear, intentionally I brought this question. Gate 16, IISc Bangalore. 2 marks question. The paper designed by IISc. Gate 16, 2 mark question it is. Okay, they have given the W average. That is, we write P average. They have written W average. Doesn't matter. Na? The power density is given. So this W average is nothing but P average. नाम में कभी कुछ नहीं होता है. You should know the meanings of the term. Right? Okay, so P average is given to you. Okay, some function C naught by R square cos power 4 theta like I gave you. Some function sin theta sin phi. I gave you. They have given directly P average. So dear, if P average is given, you know U also, na? Bhai, what is U? R square P average. Agar if you want to apply the similar previous approach, so that is R square P average. So when you multiply by R square, you only get C naught cos power 4 theta. Like previous question was 2 sin theta sin phi. Here also there is some function C naught cos power 4 theta in the radial direction. Okay, chalo. ये तो U है ना? ठीक है. So now you can proceed. Now, what is the question? What is the power radiated by the antenna? So they are asking P rad also. Okay. And what is the maximum directivity of the antenna? Directivity. They are asking D also. Acha dekho, even if they ask directivity, last question. Even if they ask directivity, last question, na, then also you need to calculate P rad. It is a hidden parameter. Even if the question is only directivity, तब भी period निकालना ही पड़ता. Integration to be handled by Wally's formula. Try it out on your own. Try it out, get 16 2 mark. अगर previous question आया है, range is slightly different. Theta is 0 से pi by 2, phi is 0 से 2 pi. Range can be anything. Look into the data. If you are done previous question, understood previous question, sure you can do it. And if there is any doubt in the previous, then you have to let me know. Then you have to let me know. The gain, so see, when I ask the question for a gain, nothing is mentioned. By default, you will always start calculating power gain if nothing is mentioned. Okay, the gain means power gain of a parabolic dish antenna. Okay, so for a parabolic dish antenna, 1 meter diameter. Okay, what is the effective area? Okay, for the parabolic dish antenna to be taken. Okay, the effective area for a parabolic dish antenna to be taken. वो भी बताऊंगा. And it has 80% efficiency. It has the 80% efficiency. The effective area for a parabolic antenna to be taken is basically given by the formula pi r square. Okay, or pi, radius is diameter by 2 क्योंकि यहाँ पे diameter given है, तो pi d by 2 whole square. Okay, pi d by 2 whole square. Okay, where d is this diameter. Okay, where d is this is the d diameter. Okay, d is this diameter of its opening. Okay, so effective area can be calculated. So this is first of all on effective area, diameter 1, so 1 by 2 ka square. So the effective area is pi by 4. Now effective area has a relation with directive gain. Effective area was given by what formula? Lambda square by 4 pi into GD. Okay, so what is lambda? Lambda भी निकालना पड़ेगा यहाँ पे. Lambda is not given, frequency is given rather. Lambda is C by F and frequency is 9.5 giga. So 3 into 10 power 8 divided by frequency is 9.5 giga, that is 10 power 9. Okay, so what is the lambda turning out to be? Let's calculate this quickly. (0.03), approximately 0.03 meters. Okay, so यहाँ से let me start calculating GD directly. 4 pi upon lambda square into the effective area, putting down the value lambda 0.03, तो इसका square किया, effective area is known as pi by 4. Okay, 4 से 4 cancel, solving up. Okay, pi square by 0.03 whole square. Okay, it's turning out to be 4 cancel though once again. Yeah, it's turning out to be a big value, but that's okay. Directive gain ही चाहिए ना? हाँ नहीं, actually then we need power gain. हाँ वो पे उस पे भी आ जाएंगे. But directivity is turning out to be 10966.22. The directive gain is turning out to be this value. एक बार check कर लेना. Okay. Now they are asking the power gain, and for that I will use the efficiency parameter. Okay, now efficiency, that is radiation efficiency by default is 0.8 and that is known as GP upon GD. So what is the GP? 0.8 of this value that was obtained, 10,966.22. So this is approximately 8772.98. Okay, so decibel में बोला है, so answer will be 10 log of this value. Answer will be 10 log of this value. Approximately 39.43. Yeah, the answer is A. Yes, approx 39 dB. Option is A. ठीक है ना? Answer is A. Answer is A, 39. dB done है. चलो next question. Okay, so in a communication system at 300 megahertz, the receiving antenna gain is 8 dB, the transmitting antenna gain is 10 dB, the transmitting power level is 25 watts, the distance between transmitter and receiver is 1 kilometer, the power received at the receiving antenna port. Transmitted power is given. Okay, the power received at the receiving antenna port, PR, to be calculated by what formula? Anybody, quickly? What formula? This is the question on PR to be calculated by Friis transmission equation, right? The Friis transmission equation. And as per the Friis transmission equation, we have PR, which is GDT GDR, product of both the power gains, lambda by 4 pi r whole square into the transmitted power. Into what? Into the transmitted power. That Friis equation after the effective area. सारा theory पहले बोल दिया था. This one, GDT GDR lambda by 4 pi r whole square into the PT. Correct? Chalo. Now, actually both the gains are given in decibel. देखो, what is given? Receiving antenna gain in decibel. That is 10 log GDR is 8. So what is GDR? It is 10 raised to the power 8 by 10. 0.8. इसको निकाल लेंगे. Similarly, transmitting antenna gain, इसको भी लिखे. That is in decibel. 10 log GDT is 10 dB. Okay, so this is simple. GDT is 10 raised to the power 1. So that is simply 10. The other value will be 6.3. GDR is 6.3. Okay, so now let's start putting the values. Okay, the power to be received at the receiving port, product of GDT, it is 10. Other one is 6.3 approximately. Okay, into lambda. Now, do I know the lambda? Okay, no, lambda nikalna padega because frequency is given to me. Okay, so what is lambda is C by F, 3 into 10 power 8 divided by 300 megahertz. Acha, ye bhi 3 into 10 power 8 ho gaya. So lambda is 1. Lambda is 1. Okay, and the distance between transmitter receiver, ye R ka value given hai. R is 1 into 10 power 3. The distance between them is 10 power 3 basically. Lambda obtained is 1 upon 4 pi, distance is 1 kilometer 10 power 3, iska whole square into the transmitted power. So the power transmitted is the transmitting power level. Okay, this is PT, power transmitted. Okay, the transmitted power level is 25 watts. 25 watts, perfect. Okay, just guys, rest is the job of your calculations. Do it up. Again, my pointer is disturbing. Yeah, what is happening today? Yeah, 9.97 10 power minus 6. 9.97 microwatts. Minute one. .97 microwatts approximately. Okay. Okay, so we have the options also. 9.97 microwatts. Option number B is very correct. Option number B is very correct answer. Chalo. Okay, so now next, if you need the discussion for antenna array, chalo wo bhi continue kar lete hain. Let's do it quickly. Let's not leave this part also. Antenna array. Okay, so when you need higher directive gains in certain directions, okay, we know that every antenna has a limitation that the radiation is a function of direction. It radiates maximum in some direction, but it radiates minute in some other directions, right? If you want more gains, more directivity in a particular direction, and if that is not possible to achieve with a single element, we make antenna arrays. We make antenna arrays. Okay, which is group of radiating elements, basically group of antenna to obtain radiation, desired radiation characteristic, commonly the directivity. Okay, an antenna array is used to obtain greater directivity, which is difficult to achieve with a single antenna element. Okay, very correct, Abid. Okay. Now, okay. So it's the array should consist of identical elements. This is not all fundamentally required, but normally for ease we take individual elements which are identical. Like all of them are Hertzian, all of them are lambda by 2 dipole. Okay. Break का कोई point ही नहीं है. I told you clearly. If we have to go non-stop, or else we have to stop. Okay, just a moment. चलो done है. Let's move ahead then. ठीक है. So now, first of all, let's start with the n element antenna array. There can be special case of 2 element array also. Okay, so n element antenna array basically comprising of n antennas, n identical antennas. थोड़ा मैं इसको simply समझा देता हूँ. Let me take this picture little simply. So what is the axis taken here? I'll follow the same. Let's say the axis taken here is the z axis. Okay, so let me take a specific z axis here. Okay, what do I mean here by this antenna array? Okay, let's say I start from origin. Okay, this is my first antenna element. Okay, I align the antenna elements as horizontally as of now. Let's say this is my second. Okay, any common example of antenna array? Yagi-Uda antenna array. Yagi-Uda antenna array. In the earlier years, okay, 90s, 80s, 90s, if you go, the commonly installed antenna at the roof of the houses for television and etc. The commonly installed antenna at the roof of the houses was Yagi-Uda. Was the Yagi-Uda. Okay, so suppose these are different antenna elements array. Okay, let's say this is the first one, and this first one, all of them for uniformity are taken equal distance from each other. Okay, are taken at equal distance from each other. That makes the total length. That makes the total length of the array. What will be the total length of the array, dear? Is it ND? What is the total length of the array? What is the total length? See, dear, if it is 2 elements, suppose if it is only 2 elements, then the distance is D. If these are 3 elements, then the total length of the array becomes 2D. If it is n elements, it is n minus 1D in general. For large value of n, ये अलग से लिख देता हूँ. It is n minus 1 into D. For large value of n, it becomes ND. Okay, but in general, it is n minus D. Okay, that is what is the length of array known as. Okay, now in sometimes you see this approximately written as ND. That is true for large n. Okay, if there are large number of antenna elements, say thousands. Okay, so then n minus 1 is approximately n. Okay, so each of the antenna element is spaced equally with the separation of D. Okay, the first one is fed with the current I0. The second one is fed with the current I0 angle alpha. So that means the current that you supply to all is identical in magnitude, equal magnitude, but there is maybe some phase difference, suppose angle alpha. And we take the phase difference as progressive phase difference, forming a progression. I0 angle alpha, I0 angle 3 alpha, etc, etc, etc. Last one will be I0 angle n minus 1 alpha. Okay. Yeah. Okay, so we say that the array is linear, arranged along a straight line. Okay, elements are spaced equally, okay, along a straight line. Okay, and it can be any axis, but here I have taken z axis. Okay, we also assume that the array is uniform. What is the meaning of this uniformity? As I told you, that each element is fed with the current of same magnitude, I0. Okay, but of progressive phase shift alpha. That is first of the current I0, the second is I0 angle alpha. Okay, the first can be I0 angle 0, then I0 angle alpha, etc, etc, etc. Okay, we are mainly interested in finding the array factor. Now why? Very important result is the total field. इस पे ध्यान रखना. The total field is the field due to a single element which is at origin multiplied by array factor. After derivation it has come up, but again we don't go to the derivation right now. But what is the more important part here is the total field at any point. The total field at any point due to the antenna array is simply equal to the field due to a single element. Now say for example, if the single element is Hertzian, you know what is mod E. If the single element is lambda by 2 dipole, then only you know what is the field. So we know the individual fields. Okay, the total field is simply the individual field of one antenna element that is at the origin multiplied by a multiplication factor that is known as array factor. And since we are talking in terms of mod E, so it will be mod of array factor. Okay, in general the total field is field due to a single element multiplied by the array factor. So majorly the questions that are there on the antenna array is commonly on the array factor. Yeah, questions around the array factor, very important parameter. So what array factor here is, the modulus of array factor after solving, okay, turns out to be the very important formula sin n xi by 2 divided by sin xi by 2. Very, very important formula. Modulus of array factor is sin n xi by 2 divided by sin xi by 2. Okay, where xi is given by beta d cos theta plus alpha. Xi is given by beta d cos theta plus alpha. Now, if you want to calculate the maxima direction of the antenna array, like we have with respect to antenna, we have already spoken what is the importance of maxima, yeah, null points, yeah, what is the HPBW, what is the main beam, yeah, major lobe known as, and etc. Okay, so if you want to maximize this total field, we need to maximize the array factor. Okay, higher the array factor, higher will be the total field. Okay, so to maximize total field, we need to maximize this quantity. So there are 2 points to note here. Okay, in this the factor xi is beta d cos theta plus alpha. As I mentioned, this will be having the maximum value of, first point. Okay, has the maximum value of n, and it is always maximum, okay, at the value when xi क्या होना चाहिए, when xi by 2 takes the value n pi, when xi by 2 takes the value of n pi, or xi equal to 2n pi. Okay, 2n pi. Okay, we can take some examples. अभी हम एक दो examples ले भी सकते हैं. Say for example, चलो, suppose if I take sometimes you can have question, find the array factor for 2 antenna array. Okay, for 2 antenna array. So what is the modulus of array factor? Then it becomes, what is the modulus of array factor then? Okay, then we have modulus of array factor equal to modulus of sin n xi by 2, that is 2 xi by 2 divided by sin xi by 2. So what is the numerator now? It is sin xi. Okay, and now I can break it as sin theta as 2 sin theta by 2. Simplify करने के लिए 2 sin theta by 2 cos theta by 2. Okay, divided by sin theta by 2. Okay, so sin theta cancelled. Okay, what is the modulus of array factor? The modulus of array factor will turn out to be 2 cos xi by 2. Now dear, you only tell me what is the maximum value of this array factor? What is the maximum value of the array factor? Okay, the maximum value of any cos theta value function is 1. The maximum value is equal to 2. The maximum value, dear, will always correspond to the value of n. And then this occurs at, this maximum will occur when? Bhai, cos 0 na. You have made cos theta as 1. Okay, ये modulus भी लगा देते हैं यहाँ पे, sorry. You have made the cos theta as 1. Now, cos theta is 1 at xi by 2 equal to 0. But not only 0, even if you take pi, listen to me. Even if you take pi, cos pi to minus 1 hota hai, but we are taking the modulus na. We are interested in magnitude value, so that also will become 1. Okay, then at 2 pi, okay, and etc. So that is why generally it will always be at xi by 2 equal to n pi. Xi by 2 equal to n pi. ठीक है. Out of the xi by 2 equal to n pi also, okay, we call the principal maxima at, principal maxima is the first value, and the principal maxima will be obtained when you take n equal to 0. As I told you, n here can be 0, 1, 2, anything. So principal maxima is obtained for n equal to 0, and principal maxima is at xi equal to 0. So if I simply say maxima, it by default means principal maxima. It by default means principal maxima. That is obtained at xi equal to 0. Okay. And then what is the maximum value of the array factor? The maximum value of the array factor will always be equal to n. Okay, it will always be equal to n. It will always be equal to n. Okay. It will always be equal to what? It will always be equal to n. Okay, ये एक point हो गया to be noted. ठीक है. Now this is for n equal to 2. अच्छा. Now next important point to be noted here. इसको भी यहीं लिखते हैं. This is the first point. इसको separate रखते हैं. Now second important point is about the null points. Is about the null points. Okay. Is about the null points. What are the null points here? The null points will be such that, okay, the null points where because see why, what is the meaning of null point here? If the modulus of array factor is 0, the total field also is 0, and wherever the total field is 0, the power also will be 0. So those will be the points where antenna is not radiating at all. Where antenna is not radiating at all. Correct. That is known as the null points, and that will be obtained, okay, as taking n xi by 2 equal to plus or minus k pi, because if you take here multiples of pi, instead of this complete angle, if you take multiples of pi here, what do you get? Okay, sine pi, sine 2 pi, sine 3 pi, all of them will become 0. Okay, you get null points. But, I'm telling you here, k is any integer. Okay, but k should not be a multiple of. K should not be a multiple of. It should not be a multiple of n. It should not be a multiple of n. देखो अगर यहीं पे मैं बोलूं, what are the null points? What are the null points here? For this particular problem only, na dear, what are the null points? Tell me. For this particular problem, what itself are the null points? Tell me. What will be the null points? So null points is obtained, okay, as cos phi by 2 becomes 0. Okay, that will be obtained at phi by 2 equal to pi by 2. Okay, phi by 2 equal to pi by 2, 90 degree. Okay, one of the cases 90 degree. Okay, or it will be equal to 3 pi by 2. Okay, or it will be equal to 5 pi by 2, etc. Okay, cos 90, cos 270, everything is 0. So what is the value of phi? Dekho, when you cancel out 2, it is pi, it is 3 pi, it is 5 pi, etc. Okay. So it is in general equal to, I can say that this is in general k pi. It is in general k pi, where k is any integer not equal to multiple of n. So what is the n here? Okay, k is not a multiple of n. Everybody okay? But 2 pi, 4 pi nahi aa raha hai na? It will never come. 2 pi, 4 pi, all these things are not coming up. Logically only you see 2 pi, 4 pi, nothing is coming up. Okay. Okay. So k can be any integer except it should not be a multiple of n. It should not be a multiple of n. Okay. Achha, now if I do activity for n equal to 3. If I do activity for n equal to 3. Dekho, agar n equal to 3 hai, so first of all, what is the modulus of array factor? It is given by modulus of sine n xi by 2, sine 3 xi by 2 divided by sine xi by 2. Okay. Now what is sine 3 theta? Sine 3 theta, 3 sine theta, okay, minus 4 sine square theta. Correct? यही identity होता है ना? Okay, 3 sine theta minus 4 sine square theta. So what is the modulus of array factor? Modulus of array factor, first term is divided, cancelled 3 वो बचा. Second में sine square is cancelled with sine. 3 sine cube, sorry, that is 3 sine cube. 3 sine theta minus 4 sine cube theta. So sine square will be left. Minus 4 sine square xi by 2. Okay, that is what is the array factor. Now dear tell me maximum kitna hoga? What is the maximum value of the array factor? So array factor is 3 minus something. Okay, to maximize, you should reduce this minus wala something. What is the minimum value of sine square? 0. Okay, because if you subtract something, answer will be less than 3. So don't subtract. That means take the other term as 0 and the maximum value is again equal to n. The maximum value will always be n. This occurs, isko 0 kab karoge? When you take 5 by 2, sine 0, pi, 2 pi, same result aa gaya na? Once again, it is n pi. When xi by 2 equal to n pi. Okay. When xi by 2 equal to the n points. Okay. Now if I am looking for null points, kindly tell me, null points kya hoga? Okay, null points, if I solve, now sometimes try to solve directly also, the null points will be obtained such that n xi by 2 equal to k pi, where k can be any integer not equal to multiple of n, matlab k not equal to 3, 6, 9, ye chhod dena, n ka value 3 hai, so 3 xi by 2 equal to k pi. Okay, so what is the value of xi? It will be 2 by 3 k pi. Okay, that means अब k का value 1 तो ले सकते हैं, तो null point will be 2 by 3 pi. K का value 2 भी ले सकते हैं, तो it will be 4 by 3. But you can't take k equal to 3. Okay, you can take k equal to 4. Okay, so that will be 2 4s are 8, directly 8 pi by 3. Okay, then k can be 5 also, so 10 pi by 3. Okay, that is the value of xi. Same means what parameter you're looking for, Malvika? What parameter you're looking for? So xi, this is the value of the xi. This is what is the value of xi. Done hai? Chalo. So null points, maxima, maximum value is n obtained at, these are the general results that I have written for you. Both of them are important. Okay, the modulus, the maximum value and the null points. The maximum value and the null points condition for array factor. Okay, so yeah, that is what is summarized. It is obtained by taking principal maxima at xi equal to 0. Forget null points bhi maine bata diya. Everything is told. Okay, everything is told. Now dekho, one more thing. As I told you, principal maxima occurs at xi equal to 0. Already discussed. Now what is the value of xi? Beta d cos theta plus alpha, and that is 0. Okay, when I take xi 0, I will get the maxima, and this will tell me the direction. See, theta is what? Since beginning we are discussing theta is the angle parameter. Okay, so I get cos theta, which is minus alpha by beta d. I get the value of cos theta, which is minus alpha by beta d. I get the cos theta, which is known as the minus alpha by beta d. Clear, everybody? Minus of alpha by beta d. Okay, so this can tell you the direction in which maxima is occurring, or sometimes the question may specify in what direction is the maxima. I need the maxima in this direction. Accordingly, you can design the antenna array because alpha and d is in your hand. Alpha and d is in your hand, right? Alpha and d is in your hand. So say for example, ये question लीजिए, ठीक है? Say for example, take this question first. Okay, there is a 6 element array. 6 element का मतलब है n, the quantity n is 6. Okay, the separation between the elements is given to you lambda by 2. There is a 6 element uniform linear array to direct maximum 60 degree of the end fire. Okay, to direct maximum at, ये language missing है, to direct the maximum I need to design an antenna array so that the maximum is obtained at 60 degree of the end fire. Okay, 60 degree of the end fire. Okay, so theta required is 60 degree. Okay, question says that we need to design an antenna which produces the maxima at theta equal to 60 degree. Okay, maybe if I use a Hertzian dipole that is producing maxima at 90 degrees. Suppose I have a single Hertzian or even lambda by 2 dipole, both are broadside I told you. Suppose I have a lambda by 2 half wave dipole, it will radiate, if this is the antenna, it will radiate maximum to the perpendicular, that is fixed. But I want to design an antenna such that I get the maximum in this particular direction, at 60 degree direction. At 60 degree direction. Okay, so if you need the maxima as this direction, Okay, maxima के लिए always one rule. Start the question with phi equal to 0. Okay, phi is known as beta d cos theta. Okay, beta d cos theta plus alpha. Okay, so now there are two parameters in your hand with respect to antenna array. Single elements are already designed and discussed. Now you can take care of the spacing between the antenna elements and you can take care about the phase shift between the currents. Ankit, alpha is with respect to the first element. Okay, alpha is with respect to the first element. Okay, whatever is phased of the first element located at origin, that has zero phase. Accordingly, you can decide the sign of alpha. Prabhanchan, alpha is not attenuation. Alpha is the phase shift between the currents that is supplied to the different elements, different antenna elements. Clear? Okay, so now D is given. So D or alpha, any one of them can be given. Next can be chosen. Okay, so D, beta can be now written in terms of lambda because D is lambda by 2. Okay, into cos theta, we want the maxima at 60, so put down theta 60 plus alpha equal to 0. Your problem is solved. Lambda, lambda cancel, 2 cancel, pi into cos 60 degrees half plus alpha, this should be 0. What is the value of alpha? Minus pi by 2. This looks a very simple question, but yet very important. This is a simple yet important question. Okay. Simple yet important question. Okay. So that is what I meant, that if you are given any direction in which you want the value of maximum radiation, okay, based on that theta, you can calculate alpha or D. These are the two elements in your hand. There's phase shift between the currents and the D. Okay, that is the spacing between the elements. Spacing between the elements. Okay. Acha. Now, like I explained you broadside antenna, there can be a broadside array also. So what is a broadside array? Which has maximum radiation directed normal to the axis of the array. Okay, so theta को 90 रखना है. Theta को 90 रखना है. So dear, if I choose theta 90 maxima के लिए, xi, which is beta d cos theta, cos 90 plus alpha equal to 0. Cos 90 0 होता है. 0 plus alpha is 0 and hence alpha will be 0. So in case if you want to design an array which is broadside, which will radiate maximum perpendicular to it, then you need to choose the current elements which are of equal phase, equal magnitude to thigh, totally equal phase. Matlab all the current elements are exactly identical, no phase difference also. No phase difference also. Correct. So alpha will be 0. You need to take care so that you have the all elements fed with the very identical currents. Very identical. Good afternoon, Chinmay. But say for example, you want a pencil beam. Now, what pencil beams look like? देखो, एक तो हमने concept देखा broadside का, okay. But now you want, suppose this is some antenna, okay. Okay, broadside direction पहले ही बनाया है. If an antenna is radiating maximum along the perpendicular to the axis, that is broadside. Okay, you may design array or antennas which may have maximum, okay, which may have maximum, okay, along the ends of this. Now, if it has maximum along the ends, now we are not only concentrated on maximum. Now, हमने क्या किया था? First we define the location of maxima, okay, and then we go around the maxima, okay, to the 3 dB points. Okay, 3 dB loss this side, 3 dB loss that side, and the separation between the 3 dB points was the HPBW, half power beam width. Anything within the HPBW is known as the major lobe, main beam. Anything within the HPBW was then defined as the main beam. Okay, let us say this is the HPBW. There will be HPBW. Okay, and anything within it was known as main beam or major lobe. Okay. Such an antenna array, or even this definition applies to single antenna also, which is radiating maximum along the ends. So at the ends you get like a pencil type beam. Kabhi wo dekha hai, you know, that pencil cracker. Pencil cracker. Tell me in the comment box. Pencil cracker. Diwali pe. Okay. एक तो होता है full जड़ी, एक pencil cracker. I've seen somebody anytime burnt pencil. I in my childhood burned it. Pencil cracker. Okay. When you light it at the other, one of the end, of course, it's only one-sided pencil. Here we are talking about bi-sided, but that is a one-sided pencil. When you light it, okay, the crackle burns something like this. You get the fire in this direction. If not seen, no problem. Somebody, किसी ने तो देखा होगा. Pencil cracker. I used to call it as pencil only. I mean, I don't know any name, but I used to call it as pencil. एक होता था simple pencil, एक होता था full जड़ी. The simplest one I'm telling you. No, not an R. Not an R. I'm talking about a pencil beam. The pencil. Google करना है pencil cracker. If there is anything else, if there is any other name, मैं आपको बताऊंगा. Okay. So, talking about pencil beam. ठीक है. चलो कुछ और नाम होगा तो मुझे नहीं पता. So this is what this looks like, a pencil beam. Okay. These are also sometimes known as the pencil beam. This antennas which radiates maximum along the ends. Now at the ends, what is the theta? 0 degree and theta 180 degree. Everything is with respect to direction theta. So at the ends theta is 0 or 180 degree. Okay. Those antenna which will be radiating maximum along the ends will be known as the end fire array. That will be the end fire array. They fire at the end. So अगर theta को 0 रखना है, maxima के लिए one condition, xi always 0, principal maxima, beta d cos 0, okay, or 180 anything, okay, plus alpha is 0. So beta d, now what is going to be cos theta dear? There will be two values, cos 0 is 1, cos 180 is minus 1, तो दोनों लिख लेते हैं, plus minus 1, plus alpha is 0. So what is the alpha? Alpha will be basically plus minus beta d. Okay, so now if you have to design a pencil beam, if you have to design an end fire array, alpha should be chosen so that it is plus minus beta d. Okay, ठीक है, तो alpha may be plus beta d or minus beta d, any of them. Okay, so end fire array, maximum radiation directed along the axis of the array, along the ends. Okay, along the ends. Okay, along the ends, and that is why theta 0 or 180 degree. Chalo, let's move here. To another important question. पहले एक important question की तरफ चलते हैं. Have a look into it. Gate 22 mark. Good question, eh? That's why I'm taking a gate question here. It's a gate 22 mark. Good question. Tell me. For an infinitesimally small dipole in free space. So, देखो, whenever we talk about small dipole, what is the thing that comes into the mind? Okay, what is the thing that comes into the mind? It's the Hertzian dipole. It is the Hertzian dipole. Okay, in free space, the electric field in the far field is proportional to e power minus jkr by r sine theta. Okay, where k is 2 pi by lambda. A vertically infinitesimally small electric dipole whose length is much smaller than lambda is placed at a distance h. Okay, above an infinite ideal conducting plane. Bhai, this question is a very good question. Mixture of two combination. What is the minimum value of h for which one of the maxima in the far field radiation pattern occurs? Okay, so one of the maxima in the far field occurs at theta 60. So we want theta 60. But is it somehow antenna array? यहाँ पे तो कोई array नहीं है. There is a single antenna element. There is a single antenna element. There is a single antenna element. बताइए. There is a single antenna element. Basically, that single antenna element as a source placed above a conducting ground plane. So this calls for method of images. This calls for method of images. Okay, so what is as per the method of images? If you apply here, if you apply method of images here, okay, so what do we do in the method of images? First of all, we remove the conducting ground plane and we assume that there is a mirror. Physically though we don't remove, but to solve, we assume that there is a mirror at that location and the role of the mirror is to create an image source. Here it is not a charge, but it is a antenna element placed here. There's an antenna element, ideal, a small antenna element has been placed at a particular height. Okay, that particular height is h. Okay, above this plane. Okay, above this plane. Then there will be, because of this, there will be image of it, similar distance पे, at a similar distance below the plate. Okay, we get the image. That is ideal. We get the image charge, we get the image antenna, that is known as the ideal. And eventually now what you have effectively is a 2-element. What do you get here is, rather than an element, here you have a 2-element array. It becomes the problem of array. It becomes the problem of array. Now you need to design the array in such a way so that you get the one of the maxima at 60 degree. Okay, at 60 degree. Okay, at 60 degree. Now let's take the angle with respect to center basically. Let's take it with respect to any point. I mean, it doesn't matter. Ye axis ho gaya. Okay, I want the maxima at 60 degree. So let me say this becomes the axis of the array. Okay, with respect to axis of the array, and the direction in which I am seeking the maxima is 60 degree. Okay, is 60 degree. So dear, what is going to be the xi factor for this? Xi is beta d cos theta plus alpha. Kya kya pata hai mujhe? Okay, the distance is now in terms of 2h. What is the distance between the arrays? Will be 2h. Okay, will be equal to 2h. Okay, so beta is 2 pi by lambda as always. H will be taken as, the distance will be 2h. Cos 60 degree plus how much? How much? Now these two elements are identical because they are just the image of each other. They are image of each other. Okay, and exact identical elements, alpha will be 0. So यहाँ पे alpha 0 हो जाएगा. Okay, this is what is xi. So what is xi? That will be equal to 4 pi h by lambda. Further, cos 60 degrees half. So that is basically 2 pi h by lambda. So now dear, very logically, if you take principal maxima, okay, if you take principal maxima, your question will not be solved. Normally maxima means we take principal maxima, xi 0, but if you take xi 0, h will also be 0, and that is wrong. Okay, very clearly mentioned that we place it at a positive height. H is greater than 0, at a distance h greater than 0. Okay, that is why the question clearly says not necessarily the principal maxima, but any one of the maxima should be at theta 60 degree. So if the principal maxima doesn't work, okay, then if the principal maxima doesn't work, then what is the general formula we have already seen? We have the maxima at xi by 2 equal to n pi. ये देख चुके हैं ना? Okay, तो what is xi by 2? Okay, okay, या इसको ऐसा बोल देते हैं, xi equal to 2n pi. Now what is that xi? 2 pi h by lambda is 2n pi. Okay, 2 pi cancelled. What is the value of h? Is n lambda. H is n lambda. अब देखो साफ बोला है minimum value of h. What is minimum value of h? So there can be several possibilities. There can be several possibilities. But what is the minimum value of h will be obtained as taking n equal to 1. Because n can be anything. 1, 2, 3, etc. 0 नहीं हो सकता because 0 वाला fail हो गया था. तो minimum height is taking n equal to 1. So the minimum height is lambda. Question solved. Method of images. अब देखो, sometimes that is what happens. You know, many times EC students, they neglect the double electrical part. They only study their, starting from wave propagation transmission line. However good antenna you might have studied, but if you don't know method of images, you are stuck. Your entire effort of antenna goes waste. So never study any subject half-hearted. And other than that, especially I will tell you two areas. If you are EC student, from the common part ECEE, there are two areas which is producing commonly very question. Number one, Gauss law. Electrostats mein Gauss law. Lot of question around Gauss law or calculation of flux, integral d dot ds pe. Gauss law and the questions around it that we have done yesterday. And next is the Biot-Savart or Ampere's law, any one of them, magnetostats. In pe question aata rehta hai. Biot-Savart law maybe that long wire. Okay, the field due to long wire. They're important. Even you see 2-marker question in the EC part. And Gauss law pe to Gauss law and the electric flux calculation, lot of questions. Okay, almost every year or every second year you're getting the question on electric pulse से Gauss law और 2 mark का होता है, उसको neglect मत करना, ठीक है. And other than that also I'm telling you there are some concepts like you may say that you are brilliant in antenna, but if you don't know method of images then this question is lost. So इसलिए पूरा अच्छे fundamentally पढ़ो, then only you are strong in the subject I feel. Okay जी. Okay जी. Tell me any doubts? Okay, चलो. In end fire array, there are 1000 elements equally spaced at a distance of quarter wavelength. What is the directivity? Now, directivity of antenna array. Dear, the directivity of antenna array, you can note down the formula here directly. It's given by 4L by lambda basically. The directivity of antenna array is basically given by the formula 4L by lambda. Okay. Now, what is L? L, as I already told you, length of the antenna, n minus d, n minus 1 into d, or approximately nd, because n is large here. Okay, क्योंकि n यहाँ पे large है, 1000 elements are there. In an end fire, there are 1000 elements coming up. That is the, चलो, when n is the number of elements, no, that we have written earlier in the form of n minus 1 only, n minus 1d, or approximately nd. Number of elements, we call it to be n, which is large. Okay, so this n is 1000. Okay, so what is the length of this array? First of all, the length of the array will be 1000 into dd is the separation, and they are equally spaced at a distance of quarter wavelength. Okay, so the separation between them is lambda by 4, clearly mentioned. So this is 250 lambda. This is known as 250 lambda. Okay, so what is the directivity then? Okay, what is the directivity then? The directivity becomes 4L. Okay, 4L, L is 250 lambda divided by the lambda, so directivity is 1000. अच्छा, dB में निकालेंगे. Options are in dB. So we have 10 log 1000. 1000 is 10 power 3. So answer will come 3 into 10, 30 dB. Log 10 will be 130 dB. Answer is D. This is 30 dB. Clear everybody? Answer is D. अच्छा, देखो, sometimes be ready, कुछ मैं homework भी देता हूँ आपको, but sometimes be ready, some questions are very fundamental. The array factor of an antenna depends on what? Quickly tell me. And it is a MSQ question. Fundamental MSQ question भी बन सकता है यहाँ से. Tell me. Tell me. What should be the answer here? Tell me, what should be the answer here? Tell me. देखो, array factor. Sin n xi by 2 divide by sin xi by 2. Okay, it depends on the number of radiating elements. Yes. Now xi depends on beta d cos theta plus alpha. So second option is spacing between the elements. Yes. It depends on the phase of the applied signal. Yes. अरे यार ये MSQ ठीक है. So it is option number D. Sorry, it's not MSQ. I thought ये वाला option नहीं है. So then it's not this. Yeah, maybe मैं इसको बना देता हूँ MSQ. चलो, we can, maybe the question is of this kind. Okay, let me write down a statement here. The array factor of an antenna element depends on option number D. Option number D. Is it also dependent on the field of the single element? It is also dependent on the field of single element. No. So it will be ABC. नहीं for MSQ फिर all of the above के साथ MSQ नहीं होगा, ठीक है? So I did not see that there is a D option, all of the above. है ना? MSQ with all of the above doesn't make any sense, na? Next. The beam width between the nulls. Beam width between the nulls. Okay, now dekho. Beam width between the nulls. Okay, between the nulls, between the first nulls basically, BWFN. Nulls means first nulls. Okay, this is also equivalent to, it's just a rearrangement. It is like first null beam width. Don't be confused. This is same as first null beam width. इसको कैसे भी बोलो. First null beam width FNBW या BWFN. Same as FNBW, that parameter already discussed. Okay, between the nulls, यहाँ पे एक और word आना चाहिए, first nulls basically. Between the first nulls of a 4-element broadside array with the half-wave dipoles. Now, what is the FNBW for antenna array? Okay, some basic formula जो बहुत ज़्यादा नहीं आते, but एक बार मैं आपको बता देता हूँ. That is basically given by 2 lambda by L. Okay, this is given by the formula 2 lambda by L. Right, 2 lambda by L. So how much it is going to become here? FNBW will be 2 lambda by L. Okay, L is again n minus 1 lambda. L is again n minus 1 lambda. Here n is not large. Okay, तो lambda lambda तो cancel हो गया. Okay, sorry, 2 n minus 1 into d. Sorry, n minus 1 into d. Now this is 2 lambda divided by n minus 1 will become 3 and d. Okay, a 4-element broadside array with half-wave dipole. So d निकालना पड़ेगा ना? Okay, we have a 4-element broadside array with half-wave dipole. What should be the d? Okay, with half-wave dipoles. Okay, tell me, what is the D for half-wave dipoles? Okay, and especially I want to design a broadside antenna array. Beta 2 pi by lambda. नहीं ऐसे generalize तो नहीं कर सकते. I think there is something missing. 2 pi by lambda beta into beta D cos 90 broadside बोल दिया है. Cos 90 that is 0. Alpha will be 0. Okay. Basically separation is not mentioned. I think that separation has to be mentioned. नहीं अंकित, how 57? Wait, D either we take it lambda by 2 या कुछ standard results नहीं ले सकते ना. 4 element है, that is okay. No, let me go to the system and check it out. नहीं lambda by 2 क्यों होगा? Let me just check it out once. Yeah, maybe some point I'm missing. Let me go to the system, just a moment. Yeah, this exactly is the question. Not mentioned. For the for the broadside array, the condition was okay, alpha should be 0. Okay, we take similar half-wave dipoles. Okay, but spacing, देखो, we have to take some spacing. No, we have to take some spacing. So let's take D equal to lambda by 4 or lambda by 2, any value you can take, not mentioned. Okay, let's take lambda by 4. Let's take it to be lambda by 4. Okay, so in that case, this becomes 2 lambda by 3, lambda by 4. Okay, and then that is equivalent to 8 by 3. Of course, this will be by default in radian. This is going to be by default in the form of radian. Correct? This is by default 8 by 3, which is in radian, and I want it in the degree. We know the conversion. Okay, we know the conversion. Pi radian corresponds to 180 degrees. So 1 radian will be 180 by pi. Okay, so approximately ये कितना आ गया? Let's check the value. $152 point something. Just check it out एक बार, है ना? Just check it out. 152.78. Okay. ठीक है, yeah. So approximately what I'm getting is 152.78. Check it out. Because data तो मैं check कर रहा हूँ. I have got the question in system. Same data is there. It's not like there is some typo error or something. Okay. अच्छा, अब ये भी देख लेना. Sometimes, you know, as I mentioned, okay, like FNBW is 2 lambda by L, okay, and that is further equal to 2 lambda by N minus 1D or 2 lambda by ND. So such questions for NAT should not be framed. Such questions for NAT should not be framed. Okay? Such questions for NAT should not be framed. Because, you know, many of the books directly use this formula ND. Okay. That should be specified value, Abid. So, you know, otherwise I think it's incomplete without that. Okay, so whatever value is mentioned, you can go around with that. If it is lambda by 2, you can go around with lambda by 2. Okay. You can go around with the lambda by 2. Okay. So, you know, such questions for NAT definitely creates confusion. So, if such question is coming, it should be MCQ most likely. Okay. Okay, because if you use ND, answer will be slightly, and it is a small n, answer will be slightly different. Slightly नहीं, completely different हो जाएगा. अगर n को 4 use किया, ये cancel हुआ. For answer is 2 radian. Okay, answer will be 2 radians. Okay, then what is the value of 2 radians? What will be the answer corresponding to 2 radians? Okay, so that's going to be 57, you know, into 214 something आएगा. Drastically different. It will not be in the range. Okay, so examiner will have to take care whether it is, you know, which formula that to be taken care. Okay, otherwise it should be a MCQ question. Acha, here, if the question, okay, this is FNBW. If the question was again HPBW, what is HPBW? The result I told you, FNBW is twice of HPBW. Okay, so if FNBW is obtained, HPBW is nothing, FNBW will be divided by 2. So you can directly then go for the formula. Okay, 2 से divide करेंगे, तो then you can use the formula lambda by L there. Okay. ठीक है जी. That is what it is. चलो. You can also take a simple password for today's session, array. A very simple password for today's session, array. That's what we were discussing at the end. Okay. You know the Telegram link already. Okay. Yesterday's PDF also is due. I know. I'll share. Yes. Pehle I'll share the yesterday's one. Okay. Then I'll share you the today's also. Okay, ji. Chalo guys, so now see you on Saturday, Sunday. Complete almost 5 hours. 5 hours, ne? 4 hours, sorry. 4 hours non-stop antenna. 4 hours of non-stop antenna discussion. Hope you liked it. Hope this is fruitful to you. Okay, do mention in the comment box later on. Also, not in the live chat box. Okay. So which are the sessions that chapters you're looking on priority? Chalo, tell me. I'll plan it. I'll plan it after maths. बताइए. चलो, if you're looking for circular waveguide, कुछ solutions तो मैं आपको बताता हूँ. Okay. There is something that I can help you immediately with. Let me know which chapters you are most importantly. First priority पे बताओ. Let me see what majority says. Which chapter out of the EMT EC part? I'll try to find out time and I'll do it. Okay. अभी तो नहीं, but after maths. Just a second. चलो जी, maybe ट्रांसमिशन लाइन्स आ रहा है, वेव गाइड आ रहा है. करेक्ट. सो देखो, वन थिंग आई विल टेल यू, वेव गाइड में ओके द न्यूली एडेड पार्ट जिसमें अभी तक क्वेश्चन नहीं आया है बाय चांस, सर्कुलर वेव गाइड. सर्कुलर वेव गाइड इज अ न्यूली एडेड पार्ट. Okay, from 2021, but yet 2021, 22, 23 question नहीं आया है. 2024 you may see a question. ठीक है. So circular waveguides I have already taken a marathon earlier. I think taken 1 or 2 years back, but sufficient to complete circular waveguide. It is a 2.5 hour session on circular waveguide only. Go and watch it. Circular waveguide आप आज ही finish कर लीजिए ना. I given you the link. I've given you the link. Okay, this is the link I've just shared you. Circular waveguide, 2.5 hour session. 2.5 hour session. So that is already solved for you. Just watch it up. You can watch it even in the fast forward. At least recording dekh rahe ho to fast forward mein dekho. Okay, the type of questions that can be there for circular waveguides, that can be covered using it easily. ठीक है. Okay, so वो कर लीजिए. Okay, then other sessions I will see. Transmission line I think is the maximum priority coming up. Of course, wave propagation question area is simple. So ठीक है, transmission lines I can plan, or maybe rectangular waveguides also. Waveguides में से circular waveguides is there in front of you. Okay, go and watch it and enjoy it completely. Circular waveguide, क्योंकि उसका content भी easily नहीं मिलेगा. It's newly added chapter. You don't find it in every textbook also, like the regular EMT. ठीक है. Yeah, of course, if I take transmission line to impedance matching, we'll see. Prabhandhan. ठीक है. So let me plan after maths. Okay जी, bye bye. Thank you. All right. Bye bye. Thank you. Stay safe. Take care. Attempt your quizzes. Okay. And Saturday, Sunday maths marathon. And other than that, okay, how to strategize maths? What are the important areas? कहाँ ज़्यादा practice करना है? So you can also join me tomorrow at 5 p.m. Okay, on the same YouTube channel. Let's discuss some important things about maths. It's going to be a small session, okay, but to take care about some important parameters. Okay, it will be there. And also guys, if you are looking to prepare for 2025 or 2026, or if you're juniors, younger brother, sister, anybody planning to prepare, so on the BYJU'S exam prep app 2025 and 26, both the courses are available, and that too in the English and Hindi, both formats. You can choose language of your comfort. Both options will be available. Okay, you can enjoy live classes with some recorded lectures, study material, mock test, practice quizzes. Okay, so you have both the options, live classes. If you're not able to attend live, you can have the recorded, also both the formats you can see. So you can see which format you want, live or recorded. All the formats are available. All the details on BYJU'S exam prep app, or if you want any further direct details, you can contact 924-133-666. Okay, and you can get all your doubts, timings, batch fee, etc. Okay, will be rectified to you. Okay. टेलीग्राम लिंक आई ऑलरेडी शेयर्ड यू कैन टेलीग्राम लिंक मैंने अभी शेयर किया था, तो उसमें PDF आ जाएगा. दैट्स इट. ओके गाइस, बाय बाय. थैंक यू. स्टे सेफ. सी यू इन द मैथ्स मैराथन एंड द मैथ्स सेशन 13 out of 13 also. Bye bye.